Welcome to this Introduction to Linux course. I'm Bo Carnes and I will be teaching this course. This course is designed for computer users who have limited or no previous exposure to Linux, whether they're working in an individual or enterprise environment. This course explores the various tools and techniques commonly used by Linux system administrators and end users to achieve their day-to-day work in a Linux environment. You will gain a good working knowledge of Linux and how to navigate through major Linux distributions, system configurations and graphical interfaces of Linux, basic command line operations, common applications of Linux, and more. Upon completion of this training, you should have a good working knowledge of Linux from both a graphical and command line perspective, allowing you to easily navigate through any of the major Linux distributions. The content of this course was developed by the Linux Foundation, who provided a grant to make this course possible. I've taken their primarily text-based course and turned it into a video-based course. Throughout the course, you will see some video segments that were developed by the Linux Foundation. Also, you should know that sometimes throughout this course, I put Linux commands on the screen like this. The $sign at the beginning is not part of the command. That just indicates the command should be typed into the system shell or terminal. So if you're following along, type everything after the $sign. In the description of this video, I've linked to a text-based version of this course. Okay, let's get started. By the end of this chapter, you should be able to describe the software environment required for this course and describe the three major Linux distribution families. In order to fully benefit from this course, you will need to have at least one Linux distribution installed. If you're not already familiar with the term distribution as it relates to Linux, you soon will be. You are about to learn some more details about the many available Linux distributions. Because there are literally hundreds of distributions, I'm not covering them all in this course. Instead, I'll focus on the three major distribution families. The families and representative distributions this course will focus on are Red Hat family systems, including CentOS and Fedora, SUSE family systems, including OpenSUSE, and Debian family systems, including Ubuntu and Linux Mint. I'm about to tell you more about Red Hat, SUSE, and Debian. While this course focuses on these three major Linux distribution families, as long as there are talented contributors, the families of distributions and the distributions within these families will continue to change and grow. People see a need and develop special configurations and utilities to respond to the need. Sometimes that effort creates a whole new distribution of Linux. Sometimes that effort will leverage an existing distribution to expand the members of an existing family. Red Hat Enterprise Linux, or RHEL, heads the family that includes CentOS, CentOS Stream, Fedora, and Oracle Linux. Fedora has a close relationship with RHEL and contains significantly more software than Red Hat's enterprise version. One reason for this is that a diverse community is involved in building Fedora, with many contributors who do not work for Red Hat. Furthermore, it's used as a testing platform for future RHEL releases. In this course, we'll mainly use CentOS Stream from the Red Hat family. The basic version of CentOS is also virtually identical to RHEL, the most popular Linux distribution in enterprise environments. However, CentOS 8 has no more scheduled updates. The replacement is CentOS 8 Stream. Some of the key facts about the Red Hat distribution family are: Fedora serves as an upstream testing platform for RHEL. CentOS is a close clone of RHEL, while Oracle Linux is mostly a copy with some changes. It supports hardware platforms such as Intel x86, ARM Itanium, PowerPC, and IBM System Z. It uses the Yum and DNF RPM-based Yum package managers to install, update, and remove packages in the system. RHEL is widely used by enterprise, which hosts their own systems. The SUSE family and the relationship between SUSE and OpenSUSE is similar to the one described between RHEL, CentOS, and Fedora. We use OpenSUSE as the reference distribution for the SUSE family, as it's available to end users at no cost. Because the two products are extremely similar, the material that covers OpenSUSE can typically be applied to SLES with few problems. Some of the key facts about the SUSE family are the SUSE Linux Enterprise Server, or SLES, is upstream from OpenSUSE. It uses the RPM-based zipper package manager, which we'll cover later, to install, update, and remove packages in the system. It includes the YAST, or Yet Another Setup Tool application for system administration purposes. SLES is widely used in retail and many other sectors. The Debian distribution is upstream for several other distributions, including Ubuntu. In turn, Ubuntu is upstream for Linux Mint and a number of other distributions. It's commonly used on both servers and desktop computers. Debian is a pure open source community project, which is not owned by any corporation, and has a strong focus on stability. And Debian provides by far the largest and most complete software repository to its users of any Linux distribution. Ubuntu aims at providing a good compromise between long-term stability and ease of use. Since Ubuntu gets most of its packages from Debian's stable branch, it also has access to a very large software repository. For those reasons, we will use Ubuntu LTS, or long-term support, as the reference to the Debian family distributions for this course. Some key facts about the Debian family are: the Debian family is upstream for Ubuntu, and Ubuntu is upstream for Linux Mint and others. It uses the dpkg-based apt package manager, which we'll cover later in detail, to install, update, and remove packages in the system. Ubuntu has been widely used for cloud deployments. While Ubuntu is built on top of Debian and is GNOME-based under the hood, it differs visually from the interface on standard Debian, as well as other distributions. So in conclusion, there are three major distribution families within Linux: Red Hat, SUSE, and Debian. In this course, we'll work with representative members of all of these families throughout. By the end of this chapter, you should be able to define the common terms associated with Linux and discuss the components of a Linux distribution. In order for you to get the most out of this course, we recommend that you have Linux installed on a machine that you can use throughout this course. You can use this brief installation guide, Preparing Your Computer for Linux Training. It will help you to select a Linux distribution to install, decide on whether you want to do a standalone pure Linux machine or a dual boot one, whether to do a physical or virtual install, and more. And then it guides you through the steps. I'll also cover installation soon. Well, we have not covered everything in great detail, but keep in mind that most of the documentation in Linux is actually already on your system in the form of man pages, which we'll discuss in great detail later. Whenever you do not understand something or want to know more about a command, program, topic, or utility, you can just type man and then the topic at the command line. So I'll just assume you're thinking this way, so I won't constantly repeat, "For more information, look at the man page for this topic." On a related note, throughout the course, we'll use a shorthand that is common in the open source community. When referring to cases where the user has to make a choice of what to enter, like a name of a program or file, we'll use the shorthand foo to basically represent insert file name here. So we're not actually suggesting that you manipulate files or install services called foo. The best way to learn Linux is by doing it. So make sure to try things out yourself as you follow along. You'll need to have a Linux system up and running that can either be a native Linux system on your hardware, running through a live USB stick or CD, or a virtual machine running through a hypervisor. We'll show you all these methods, so let's get going.
Before you begin using Linux, you need to be aware of some basic terms, such as kernel, distribution, bootloader, service, file system, X window system, desktop environment, and command line. These are very commonly used by the Linux community. The kernel is considered the brain of the Linux operating system. It controls the hardware and makes the hardware interact with the applications. An example of a kernel is the Linux kernel. The most recent Linux kernel, along with past Linux kernels, can be found at the kernel.org website. A distribution, also known as distros, is a collection of programs combined with the Linux kernel to make up a Linux-based operating system. Some common examples of a distribution are Red Hat Enterprise Linux, Fedora, Ubuntu, and Gentoo. The bootloader, as the name implies, is a program that boots the operating system. Two examples of a bootloader are Grub and ISO-Linux. A service is a program that runs as a background process. Some examples of the service are HTTPD, NFSD, NTPD, FTPD, and named. A file system is a method for storing and organizing files in Linux. Some examples of file systems are ext3, ext4, FAT, XFS, and ButterFS. The X window system provides the standard toolkit and protocol to build graphical user interfaces on nearly all Linux systems. The desktop environment is a graphical user interface on top of the operating system. GNOME, KDE, XFCE, and Fluxbox are some examples of the desktop environment. The command line is an interface for typing commands on top of the operating system. The shell is the command line interpreter that interprets the command line input and instructs the operating system to perform any necessary tasks and commands. For example, bash, tc shell, and z shell.
Suppose you have been assigned to a project building a product for a Linux platform. Project requirements include making sure the project works properly on the most widely used Linux distributions. To accomplish this, you need to learn about the different components, services, and configurations associated with each distribution. We're about to look at how you would go about doing exactly that. So, what is a Linux distribution and how does it relate to the Linux kernel? The Linux kernel is the core of the operating system. A full Linux distribution consists of the kernel plus a number of other software tools for file-related operations, user management, and software package management. Each of these tools provides a part of the complete system. Each tool is often its own separate project with its own developers working to perfect that piece of the system. While the most recent Linux kernel and earlier versions can always be found in the Linux kernel archives, Linux distributions may be based on different kernel versions. For example, the very popular RHEL 8 distribution is based on the 4.18 kernel, which is not new but is extremely stable. Other distributions may move more quickly in adopting the latest kernel releases. It's important to note that the kernel is not an all-or-nothing proposition. For example, RHEL and CentOS have incorporated many of the more recent kernel improvements into their older versions, as have Ubuntu, OpenSUSE, SLES, and more. Examples of other essential tools and ingredients provided by distributions include the C and C++ and Clang compilers, the GDB debugger, the core system libraries applications need to link with in order to run, the low-level interface for drawing graphics on the screen, as well as the higher-level desktop environment and the system for installing and updating the various components, including the kernel itself. And all distributions come with a rather complete suite of applications already installed. The vast variety of Linux distributions are designed to cater to many different audiences and organizations, according to their specific needs and tastes. However, large organizations, such as companies and governmental institutions and other entities, tend to choose the major commercially supported distributions from Red Hat, SUSE, and Canonical, which is Ubuntu. CentOS and CentOS Stream are popular free alternatives to Red Hat Enterprise Linux, RHEL, and are often used by organizations that are comfortable operating without paid technical support. Ubuntu and Fedora are widely used by developers and are also popular in the educational realm. Scientific Linux is favored by the scientific research community for its compatibility with scientific and mathematical software packages. Both CentOS variants are binary compatible with RHEL, which means in most cases binary software packages will install properly across the distributions. Many commercial distributors, including Red Hat, Ubuntu, SUSE, and Oracle, provide long-term fee-based support for their distributions, as well as hardware and software certification. All major distributions provide update services for keeping your system primed with the latest security and bug fixes and performance enhancements, as well as provide online support resources. You have completed Chapter 2. Let's summarize the key concepts covered. Linux borrows heavily from the Unix operating system, with which its creators were well versed. Linux accesses many features and services through files and file-like objects. Linux is a fully multitasking, multi-user operating system with built-in networking and service processes known as daemons. Some of the more common terms used in Linux are kernel, distribution, bootloader, service, file system, X-Window system, desktop environment, and command line. And a full Linux distribution consists of the kernel plus a number of other software tools for file-related operations, user management, and software package management. By the end of this chapter, you should be able to identify Linux file systems, identify the differences between partitions and file systems, describe the boot process, and install Linux on a computer. The Linux boot process is the procedure for initializing the system. It consists of everything that happens from when the computer is first switched on until the user interface is fully operational. Having a good understanding of the steps in the boot process may help you with troubleshooting problems, as well as with tailoring the computer's performance to your needs. On the other hand, the boot process can be rather technical, and you can start using Linux without knowing all the details. Starting an x86-based Linux system involves a number of steps. When the computer is powered on, the basic input-output system, or BIOS, initializes the hardware, including the screen and keyboard, and tests the main memory. This process is also called POST, Power-on Self-Test. The BIOS software is stored on a ROM chip on the motherboard. After this, the remainder of the boot process is controlled by the operating system. Once the POST is completed, the system control passes from the BIOS to the bootloader. The bootloader is usually stored on one of the hard disks in the system, either in the boot sector for traditional BIOS or MBR systems, or the EFI partition for more recent or unified extensible firmware interfaces or EFI/UFI systems. Up to this stage, the machine does not access any mass storage media. Thereafter, information on date, time, and the most important peripherals are loaded from the CMOS values, after technology used for the battery-powered memory store, which allows the system to keep track of the date and time even when it's powered off. A number of bootloaders exist for Linux. The most common ones are Grub for Grand Unified Bootloader, ISO-Linux for booting from removable media, and DOS U-Boot for booting on embedded devices appliances. Most Linux bootloaders can present a user interface for choosing alternative options for booting Linux, and even other operating systems that might be installed. When booting Linux, the bootloader is responsible for loading the kernel image and the initial RAM disk or file system into memory. The bootloader has two distinct stages. For systems using the BIOS MBR method, the bootloader resides at the first sector of the hard disk, also known as the master boot record. The size of the MBR is just 512 bytes. In this stage, the bootloader examines the partition table and finds a bootable partition. Once it finds a bootable partition, it then searches for the second stage bootloader, for example Grub, and loads it into RAM. For systems using the EFI/UEFI method, UEFI firmware reads its boot manager data to determine which UEFI application is to be launched and from where. The firmware then launches the UEFI application, for example grub, as defined in the boot entry in the firmware's boot manager. The second stage bootloader resides under /boot. A splash screen is displayed which allows us to choose which operating system to boot. After choosing the OS, the bootloader loads the kernel of the selected operating system into RAM and passes control to it. Kernels are almost always compressed, so its first job is to uncompress itself. After this, it will check and analyze the system hardware and initialize any hardware device drivers built into the kernel. The init-ram-fs file system image contains programs and binary files that perform all actions needed to mount the proper root file system, like providing kernel functionality for the needed file system and device drivers for mass storage controllers with a facility called udev for user device, which is responsible for figuring out which devices are present, locating the device drivers they need to operate properly, and loading them. After the root file system has been found, it's checked for errors and mounted. The mount program instructs the operating system that a file system is ready for use, and associates it with a particular point in the overall hierarchy of the file system, the mount point. If this is successful, the init-ram-fs is cleared from RAM and the init program from the root file system is executed. Init handles the mounting and pivoting over to the final real root file system. If special hardware drivers are needed before the mass storage can be accessed, they must be in the init-ram-fs image. Near the end of the boot process, init starts a number of text mode login prompts. These enable you to type your username followed by your password and to eventually get a command shell. However, if you're running a system with a graphical login interface, you'll not see these at first. Usually the default command shell is bash, but there are a number of other advanced command shells available. The shell prints a text prompt indicating it is ready to accept commands. After the user types the command and presses enter, the command is executed, and another prompt is displayed after the command is done. The bootloader loads the kernel and an initial RAM-based file system into memory so it can be used directly by the kernel. When the kernel is loaded in RAM, it immediately initializes and configures the computer's memory. It also configures all the hardware attached to the system. This includes all processors, I/O subsystems, storage devices, and more. The kernel also loads some necessary user space applications. Once the kernel has set up all its hardware and mounted the root file system, the kernel runs the sbin/init. This then becomes the initial process, which then starts other processes to get the system running. Most other processes on the system trace their origin ultimately to init. Exceptions include the so-called kernel processes. These are started by the kernel directly, and their job is to manage internal operating system details. Besides starting the system, init is responsible for keeping the system running and for shutting it down cleanly. One of its responsibilities is to act when necessary as a manager for all non-kernel processes. It cleans up after them upon completion and restarts user login services as needed when users log in and out, and does the same for other background system services. Traditionally, this process startup was done using conventions that date back to the 1980s and the System V variety of Unix. This serial process had the system passing through a sequence of run levels containing collections of scripts that start and stop services. Each run level supported a different mode of running the system. Within each run level, individual services could be set to run or to be shut down if running. However, all major distributions have moved away from this sequential run-level method of system initialization, although they usually emulate many System V utilities for compatibility purposes. Next, we'll discuss the new methods of which systemd has become dominant. Systems with systemd start up faster than those with earlier init methods. This is largely because it replaces a serialized set of steps with aggressive parallelization techniques, which permits multiple services to be initiated simultaneously. It has been adopted by all major distributions, and so we'll not discuss the older systemd method or upstart, which has become a dead end. Complicated startup shell scripts are replaced with simpler configuration files, which enumerate what has to be done before a service is started, how to execute service startup, and what conditions the service should indicate have been accomplished when startup is finished. One thing to note is that sbin/init now just points to lib/systemd/systemd. So systemd takes over the init process. One systemd command, system control, is used for most basic tasks. While we have not yet talked about working at the command line, here's a brief listing of its use. Think of a refrigerator that has multiple shelves that can be used for storing various items. These shelves help you organize the grocery items by shape, size, type, etc. The same concept applies to a file system, which is the embodiment of a method of storing and organizing arbitrary collections of data in a human usable form. Different types of file systems supported by Linux include conventional disk file systems, flash storage file systems, database file systems, and special purpose file systems. This section will describe the standard file system layout shared by most Linux distributions. A partition is a physically contiguous section of a disk, or what appears to be so in some advanced setups. A file system is a method of storing or finding files on a hard disk, usually in a partition. One can think of a partition as a container in which a file system resides, although in some circumstances a file system can span more than one partition if one uses symbolic links, which we'll discuss much later. A comparison between file systems in Windows and Linux is shown in this table. Linux systems store their important files according to a standard layout called the File System Hierarchy Standard, which has long been maintained by the Linux Foundation. Having a standard is designed to ensure that users, administrators, and developers can move between distributions without having to relearn how the system is organized. Linux uses the / character to separate paths, unlike Windows, which uses the \, and it does not have multiple drive letters. Multiple drives and/or partitions are mounted as directories in the single file system. Removable media, such as USB drives and CDs and DVDs, will show up as mounted at run/media/your username/disk label for recent Linux systems, or under /media for older distributions. For example, if your username is student, a USB pin drive labeled Fedora might end up being found at run/media/student/Fedora. And a file readme.txt on that disk would be at run/media/student/Fedora/readme.txt. All Linux file systems are case sensitive, so these different ways of spelling boot represent 3 different directories or folders. Many distributions distinguish between core utilities needed for proper system operation and other programs, and place the latter in directories under /usr or user. Now let's learn about viewing the file system hierarchy from the graphical interface in Ubuntu.
Click the File Manager icon on the left panel. By default, it explores your home directory. To see all directories under Root Directory, click Computer on the left Places pane inside this window. Double-click the etc directory to open it. Double-click Avahi and press Ctrl-L to see the current location. The current path appears at the top of the window. The path for this is etc Avahi.
Now let's learn about viewing the file system hierarchy from the graphical user interface in OpenSUSE.
Click Activities on the top left corner of the screen corner. Click the File Manager icon on the left panel. By default, it explores your home directory. Click Computer on the left Places pane inside this window. You can see all directories under the root directory. Double-click the etc directory to open it. To see the current location, double-click the Avahi folder and press Ctrl-L. The current path appears at the top of the window. The path for this is etc Avahi.
Suppose you intend to buy a new car. What factors do you need to consider to make a proper choice? Requirements which need to be taken into account include the size needed to fit your family in the vehicle, the type of engine and gas economy, your expected budget and available financing options, reliability record and after-sales services, etc. Similarly, determining which distribution to deploy also requires planning. Here you can see some, but not all, choices. Note that many embedded Linux systems use custom-crafted contents rather than Android or Yocto. Some questions worth thinking about before deciding on a distribution include: what is the main function of the system? What types of packages are important to the organization? For example, web server, word processing, etc. How much hard disk space is required and how much is available? For example, when installing Linux on an embedded device, space is usually constrained. How often are packages updated? How long is the support cycle for each release? For example, LTS releases have long-term support. Do you need kernel customization from a vendor or a third party? What hardware are you running on? For example, it might be x86, ARM, or PPC. Do you need long-term stability? Can you accept or need a more volatile, cutting-edge system running the latest software? The partition layout needs to be decided at the time of installation. It can be difficult to change later. While Linux systems handle multiple partitions by mounting them at specific points in the file system, and you can always modify the design later, it's always easier to try to get it right to begin with. Nearly all installers provide a reasonable default layout, with either all space dedicated to normal files on one big partition and a smaller swap partition, or with separate partitions for some space-sensitive areas like home and var. You may need to override the defaults and do something different if you have special needs, or if you want to use more than one disk. All installations include the bare minimum software for running a Linux distribution. Most installers also provide options for adding categories of software. Common applications such as the Firefox web browser and LibreOffice Office Suite, developer tools like the V and Emacs text editors, which we'll explore later, and other popular services such as the Apache web server tools or MySQL database are usually included. In addition, for any system with a graphical desktop, a chosen desktop such as GNOME or KDE is installed by default. All installers set up some initial security features on the new system. One basic step includes setting the password for the superuser, root, and setting up an initial user. In some cases, only an initial user is set up. Direct root login is not configured, and root access requires logging in first as a normal user and then using sudo, as we'll describe later. Some distributions will also install more advanced security frameworks, such as SE-Linux or AppArmor. For example, all Red Hat-based systems, including Fedora and CentOS, always use SE-Linux by default, and Ubuntu comes with AppArmor up and running. Like other operating systems, Linux distributions are provided on removable media, such as USB drives and CDs or DVDs. Most Linux distributions also support booting a small image and downloading the rest of the system over the network. These small images are usable on media or as network boot images, in which case it is possible to perform an install without using any local media. Many installers can do an installation completely automatically using a configuration file to specify installation options. This file is called a Kickstart file for Red Hat-based systems, an AutoYAS profile for SUSE-based systems, and a pre-seed file for Debian-based systems. Each distribution provides its own documentation and tools for creating and managing these files. The actual installation process is pretty similar for all distributions. After booting from the installation media, the installer starts and asks questions about how the system should be set up. These questions are skipped if an automatic installation file is provided. Then the installation is performed. Finally, the computer reboots into the newly installed system. On some distributions, additional questions are asked after the system reboots. Most installers have the option of downloading and installing updates as part of the installation process. This requires internet access. Otherwise, the system uses its normal update mechanism to retrieve those updates after the installation is done. The demonstrations we'll see show how to install Linux directly on your machine, erasing everything that was there. While the demonstrations will not alter your computer, following these procedures in real life will erase all current data. There are also alternate methods to install Linux where you won't lose any data. So some of those methods include repartitioning your hard disk to free up enough room to permit dual boot or side-by-side installation of Linux, along with your present operating system, or using a host machine hypervisor program, such as VMware's products or Oracle VirtualBox, to install a client Linux virtual machine. And finally, booting off of and using a live CD or USB disk and not writing to the hard disk at all. The first method is sometimes complicated and should be done when your confidence is high and you understand the steps involved. The second and third methods are quite safe and make it difficult to damage your system. Here are the steps to install Ubuntu.
Now going to do an install of Ubuntu 18.04 as a virtual machine under the VMware hypervisor using a Red Hat 7 host system running VMware Player. So first thing we need to do is to create a new virtual machine. And for that, I already have the Ubuntu install disk mounted in the virtual CD drive, and we'll give it a name for the user as LF student with a username of student, and we have to give a password, which I've done. And then for the name, let's just call it Ubuntu, and then on the host machine I want to have a certain place I want to put it. Rather than my home directory, I want it on a disk that has a lot of space. And then let's allocate 30 gigabytes of space. And I prefer to have it as one big file rather than multiple files or slices. I find that clutters my system less. And really that's all you have to do to start setting up the install. But it's better to click on Customize Hardware and increase the amount of memory from 1 gigabyte to 4 in my case. And I might as well take advantage of having multiple processors, so I'll let it use all 4 processors on this host machine. And then I'll just click on Finish, and it will start the install after a couple of harmless messages about how the virtual machine graphics driver doesn't permit accelerated graphics performance. Now, the beautiful thing about the Ubuntu install on this recent version is that I am done. There are no more choices to make. I don't have any more parameters to specify, etc. If I hadn't been installing in a virtual machine, it would have asked me information like username and password at this stage, but it was able to pick that up because of intelligent way that VMware can handle Ubuntu. So I'm doing this in real time. If you can read the messages, you see it just created the main file system on the system, and now it's going through the stage of copying all the files over to the hard disk, or I should say the simulated hard disk. Now this takes a little bit of time, so I'll pause the recording for a few seconds so you don't have to watch not much happening. It skipped about a minute or so, and now it says it's almost finished copying files. It's showing a bunch of different blurbs for various features in this Bionic Beaver or Ubuntu 18.04 release. The status bar has reached all the way to the right, so it should be almost done. And now it's doing the actual install of the system. So it's copied all the files it needs over to the hard disk, and it's doing the actual configuration. So once again, I believe I'll pause for a little while so you don't have to sit here and watch not much happening. Pause for about a minute. Now it says it's configuring hardware. So it's finding all the hardware devices in the system, making sure it has the right device drivers for it, etc. It's now configuring the bootloader, the grub, and now it's doing cleanup. It's getting rid of packages which were only needed during the install. And of course that's rolling by far too fast to be readable. And so it's doing a little bit more package installation. I think I'll pause again for a little while. So it reached the end of the status bar, and now it's doing the reboot. And shortly I should be getting a login prompt. If you notice, it's installing OpenVM Tools. That's a package of special drivers and configuration stuff that's used when you're running it as a guest under VMware Hypervisor. And we've reached the login screen running under the greeter. So I'll just log in as student. And oops, I typed in the wrong password, I suppose. Yep. And now the system's running. There's a few introductory messages here, and I'll just click through them to get to a fully up system. And then just to see what really happened here, if I right click, I can open up a terminal, and then I'm going to run the command df for disk-free -t to show me what type of file systems I have, and h to print out the results in megabytes and gigabytes. And I see that in the main file system I have 30 gigabytes of space, of which I'm using 5.3, and it's an ext4 file system. When we install CentOS, we need to actually specify the type of file system, the size of the partition, etc. But Ubuntu made choices that it thought were best. Likewise, we won't talk about this now, but if I look at swap files, you'll see that there is a swap file of about 1.5 gigabytes created instead of a swap partition. Usually distributions create swap partitions. So that's all there is to install the latest version of Ubuntu. Absolutely nothing to do during the install. It makes what it thinks is sensible decisions for everything. And after the system is up and running, you can then go into the package manager and put in exactly what you need and configure the system in other ways. If you need a more flexible installation to begin with, you can make such choices when you start, but we took the easy path here.
Here are the steps to install CentOS.
We are now going to do a fresh install of CentOS 8.1, the latest version of CentOS at the time of this installation. We have already allocated hard disk space for this installation to make a virtual machine under VMware, and we have inserted the install disk image, and we are ready to begin. So we will not take the step of testing the media and installing it because that takes some time. So we'll just go directly to an install. So I'll just move to the first element here and hit return. And we'll try to do this install as quickly as possible. So we'll choose mostly the default choices. And we're going to do a workstation install rather than a server install because this is what is desired for this course, to have a user-based install. Okay, so the first choice is to pick the language. We'll pick English. And then we can go really through any order we want through these different choices to begin with, but let's just go in order. So we've already picked an English keyboard with the US layout. And also language support is set up for English for the United States. You can click on these to make those changes. For the time and date, it's actually better to make sure the network is installed first. So here I clicked on network, and I'm going to turn on the network. It found the network card, and it's kind of ready to go. Probably should configure, but I think the default choices will be fine. If I go to General, it says all users may connect. And then if I go to IPv4 settings, you'll see it's automatic DHCP. So that's generally what you want rather than having to give it a fixed address. So we'll just say OK for all this. And I guess we should say connect automatically with priority 0. That means it'll always connect when you start up the machine, and we can say done. The reason it's good to do that before we set the time and date is we can now have network time on, which means it will automatically find the time. I'm currently doing this installation from Central Time Zone in the United States, so you can try to do that with the mouse. And I got it right. It's set for Chicago, which is Central Time. So I'll say done. And then the installation source is rather important, but that's local media. I already have the DVD set. As you see, it's CentOS 8-1-1911. That's the latest version of CentOS. For the software selection, let's just keep the workstation. I could make it a server with a graphical interface or just a server. If I really wanted to be quick, I could do a minimal install and then bring everything up later that I need. But within the workstation, I should pick a few things. So I'll pick GNOME applications, Internet applications. You'll probably want to pick the Office Suite and productivity, but I'd like this to go quickly, so I won't do that right now. I'll pick development tools in case I want to compile anything. And that's probably the main things I need right now, but you can always change everything in detail once the system's up. So it's good to do a relatively quick install. The trickiest part here is to do the installation partitioning setup. So I've already got picked here the virtual 30 gigabyte disk. And if I wanted to make things really fast, I would do automatic storage configuration and let it decide what kind of partitions I should have, how big they should be, etc. And you may want to at least look at that, but let me just do custom because it fits in better with my needs. And then I can say done. Okay, and then I get to pick what kind of installation. I want to do a standard partition and not an LVM, which is logical volume management. I just want a simple standard partition, so I'll do that. And then I actually have to create the partitions I need, so I hit the plus sign. And I'll have one big partition for everything, so it's mounted at slash. And let's give it 29 gigabytes. And I'll add that. This is the 30 gigabyte disk. And then I'll add one more, okay? And that won't be mounted, that'll be for swap. And if I don't give it desired capacity, it should take it all. Which it actually decided it should have 3 gigabytes. I'll let the system go with what it wants. It's doing that based on how much memory I have, okay? And it says I have only like 1 megabyte left out of the total 30 gigabytes. The one other thing I get to do for the first mount point here is pick what kind of file system. And you notice the default on Red Hat now is, or CentOS, is XFS. Let me make it ext4, which is easier to mount from other machines, etc. than XFS. But you can just take the default if you prefer, and then I say done, and it should be done. It's telling me, do I really want to do this, because it's going to wipe out everything that's on that disk? And I'll say sure, accept the changes. So I'm pretty much done. KDump is a system you can set up so that if the system crashes, you produce what's called a core dump file. So I'll just, you probably won't need to use that. It'll be a little faster to boot when you have a new kernel, so I'll just not enable that. But if you're doing a developed machine, you probably want that. We already configured the network, and under security policy, we won't do any specialization. We'll just leave it alone for now. You can always change it later, and then you just say begin installation. Now, it'll already take a head start on trying to load some packages and files while you have some more information to put in. First, you'll have to pick a password for the root account, and so I'll do that. And it's actually lftrain for virtual machines we use for the classes, which is a pretty simple password. And it's hard to read here, but it should be saying it's too simple. I can't see that. Oh, it says weak here, but it says press done again to use the password anyway, so I'll do that. This is a throwaway machine. And then I have to create a user. I'll make the full name of the user LF student. And by choice, by default, it wants to make the username of the account L student, but we'll just make it student. It will require a password to use this account. If we said make this user administrator, it would be like Ubuntu systems where there's just one password and you have to do sudo to do anything privileged, but let's keep a standard Unix type setup with separate accounts and passwords for the student user and the root user. So we're going to give a very simple password again, just the word student. And once again, it's, it says it does not match. I must have typed things wrong. Let's try again, student, student. Yeah, so now it says the password contains the username in some form. You will have to pass done twice to confirm it. It's also considered very weak, but we'll accept it. Once again, it's a throwaway machine. In real life, you shouldn't do this. And so I say done. And now we just have to wait for the install. You'll see it has installed 500 some odd packages out of 1481. We could keep watching while this happens, but it takes some time, so I'm going to pause the recording and come back when it's almost done. So it has finished and it's configuring the kernel now. That takes a little bit of time. It installed, I think, 1481 packages. So now it's doing the actual configuration of the kernel. It is doing a few other configuration steps. You'll notice it is installing the bootloader, it configured the editors, is generating what's called the init ramfs, which is needed to boot. It contains the initial file system, which is stored in memory just for the system booting, which we talk about in detail in this course. And this is probably the last thing it really has to do before it's done. Depending on the complexity of things, it can take a while. It is now complete. So now we can simply reboot. So let's do that. And we should have a running system. And you see it wants to boot there into the default kernel, 4.18.0. And I didn't do anything. It will automatically boot on its own. And then there's a few things that happen when you start up the first time. It wants me to accept the end user license, which is pretty simple for an open source product. And then finish configuration. It has a few other things to set up. And we're ready to do our first login as student. So I clicked on that. I type in the password. Then we have an up and running system, and it's going to ask us to confirm again our choice of language. And we could check to make sure the keyboard is okay, but we're fine with English US. And I'm going to turn off location services. That's a choice you can make. And if you want, you can connect to various online accounts. We're going to skip all that. And we're ready to go. So now we have a fully functional system. It brings up a tutorial screen if you want to get some more information. We'll just skip that. And here we are. It's a fully functional system. If I want to get a little information, let me drop to a command line. So I clicked on Activities. I'll say Terminal, and here we are. So for instance, if I do df-h, you'll see I've used 5.2 gigabytes, and there's plenty of space available. If I wanted to change the size of the screen, depending on your hypervisor, sometimes you can just kind of drag it out or something, but here, let me go to display settings, and it's set for 1280 times 768. And I obviously can go bigger, so just to show you, for instance, let's say I take 1920 by 1220, and I'm filling up the whole screen now. It's actually bigger than my whole screen, so I'll revert to settings. But you can do all sorts of other adjustments, and we've done a complete install of CentOS 8. It's all set and ready to use and customize to your heart's content.
Here are the steps to install OpenSUSE.
We are now going to do a fresh install of OpenSUSE as a virtual machine under a VMware hypervisor on a Red Hat 7 system. We have already inserted the install DVD, and we are about to begin. Notice that in our initial screen we can do an installation, an upgrade, or if we scroll down to more, we see that we can also use the install DVD as a rescue system. We can check memory and do various things, but we're going to do an install. So I'll just click on install, and then it will cook for a while before it asks me to do anything. So now it's finding all the hardware, deciding what drivers to use, etc., and getting started. This is OpenSUSE Leap version 42.3. And this is a typical GNOME graphical booting screen while it's getting itself ready. It should take a few more seconds. I'll pause so we don't have to watch the whole thing. Okay, it has moved on and it's about ready to bring up a graphical screen. And there we go. So it's initializing the hardware on the system. Okay, now it's asking whether we want to accept English as a language. and also the license agreement. So we'll just say sure. Click on the next button. It's doing more probing of the system, deciding what to do. And it says in a very small font, initializing the installation. Now it would like to take a default partition scheme, which we will override. So let me say edit proposed settings, and I will take a partition-based proposal. I will choose for my root partition ext4. I won't have any separate home partition or other partitions to keep things simple, and that's all I have to choose. So it's pretty simple. And it says here it's going to create a swap partition of 2 gigabytes and then a root partition for everything else of 28 gigabytes. And so I'm happy enough with that, so I'll just say next. And first thing is just to pick the time zone, so I'll pick Central Time, where I am currently sitting. And I could do some other settings. Do that unless I don't want to take automatic time setting. So I just say next. And here I have a choice for what kind of desktop. Let me pick the GNOME desktop. I could pick the KDE, or as a server, pure text mode, no graphical, or I could do custom to do something a little more complicated or different. And then it wants me to give a full name for the main user, so I'll say LF student. And for username, I'll pick student, and I'll give a password. And then I will not use this password for system administrator. That would be like what Ubuntu does. And I will not pick automatic login. It's generally not a good idea to let your system log in without having to give a password. So I'll say next. It doesn't like my password because it's too simple, but I'll say, okay, do it. And now I have to give a root password. And you might want to test your keyboard layout to make sure you have the right language. I'll say next. And once again, it's going to complain my password is too simple. And then I just say install. And that's all the choices that I actually have to make. So they really nothing except specifying username, password, and what kind of desktop I want. We can do further adjustments once the system is fully installed. Now, while it's installing, which should take about 10 minutes, the default screen here is a slideshow giving you brochures and information. If I click on details, it's a little more fun to look at. So you can see the overall progress as it goes. This first bar here is for each package as it's being installed, and on the bottom you can see I'm already about 15% installed. So I'm going to pause the recording because it's kind of boring to watch it install all 1,500 packages, and I'll wait until it's asking me to do something again before resuming. Okay, that took about less than 10 minutes, and now it's telling me the system is going to reboot, and it did. And so we'll just see our normal booting of the new open SUSE system. And it should quickly bring up the login screen. Just a few more seconds. And there's our usual greeter screen. I'll just type in the password for the student account. And we have a fully operational OpenSUSE system. Now the first thing I would do from here is update the system, because there's always new updates to various packages since the DVD install disk was released. So that's important for both security and performance. And it's even prompting me to go ahead and do that. And then I'd probably do some minor customizations about what kind of menus I see, how Windows behave, the keyboard, etc. But I'll leave that for people to do as an exercise.
You have completed Chapter 3. Let's summarize the key concepts covered. A partition is a logical part of the disk. A file system is a method of storing or finding files on a hard disk. By dividing the hard disk into partitions, data can be grouped and separated as needed. When a failure or a mistake occurs, only the data in the affected partition will be damaged, while data on the other partitions will likely survive. The boot process has multiple steps, starting with the BIOS, which triggers the bootloader to start up the Linux kernel. From there, the init-ram-fs file system is invoked, which triggers the init program to complete the startup process. And determining the appropriate distribution to deploy requires that you match your specific system needs to the capabilities of the different distributions. By the end of this chapter, you should be able to manage graphical interface sessions, perform basic operations using the graphical interface, change the graphical desktop to suit your needs. You can use either a command line interface or a graphical user interface when using Linux. To work at the CLI, you have to remember which programs and commands are used to perform tasks. On the other hand, using the GUI is often quick and easy. It allows you to interact with your system through graphical icons and screens. For repetitive tasks, the CLI is often more efficient, while the GUI is easier to navigate if you don't remember all the details or do something only rarely. We'll learn how to manage sessions using the GUI for the 3 Linux distribution families that we cover the most in this course, which are Red Hat, including CentOS and Fedora, SUSE, OpenSUSE, and Debian, Ubuntu and Mint. In subsequent sections of this course, we'll concentrate in great detail on the command line interface, which is pretty much the same on all distributions. Generally, in a Linux desktop system, the X Windows system is loaded as one of the final steps in the boot process. It's often just called X. A service called the Display Manager keeps track of the displays being provided and loads the X server, so-called because it provides graphical services to applications, sometimes called X clients. The Display Manager also handles graphical logins and starts the appropriate desktop environment after a user logs in. X is rather old software. It dates back to the mid-1980s, and as such, it has certain deficiencies on modern systems, for example with security. And it's been stretched rather far from its original purpose. A newer system, known as Wayland, is gradually superseding it and is the default display system for Fedora, RHEL 8, and other recent distributions. For the most part, it looks just like X to the user, although under the hood it's quite different. A desktop environment consists of a session manager, which starts and maintains the components of the graphical session, and the window manager, which controls the placement and movement of windows, the window title bars, and controls. Although these can be mixed, generally a set of utilities, session manager, and window manager are used together as a unit, and together they provide a seamless desktop environment. If the display manager is not started by default in the default run level, you can start the graphical desktop in a different way, after logging into a text mode console by running start X from the command line. When you install a desktop environment, the X display manager starts at the end of the boot process. It's responsible for starting the graphics system, logging in the user, and starting the user's desktop environment. You can often select from a choice of desktop environments when logging into the system. GNOME is a popular desktop environment with an easy-to-use graphical user interface. It's bundled as the default desktop environment for most Linux distributions, including Red Hat Enterprise Linux, RHEL, Fedora, CentOS, SUSE Linux Enterprise, Ubuntu, and Debian. GNOME has menu-based navigation and is sometimes an easy transition to accomplish for Windows users. However, as you'll see, the look and feel can be quite different across distributions, even if they're all using GNOME. Another common desktop environment, very important in the history of Linux and also widely used, is KDE, which has often been used in conjunction with SUSE and OpenSUSE. As previously mentioned, most desktop environments follow a similar structure to GNOME, and we'll restrict ourselves mostly to it to keep things less complex.
Let's demonstrate how we log in and log out of a system which has already been booted. On all recent distributions, this looks pretty much the same. Here we're showing an instance of CentOS Stream, which has 3 users on the system. And I can log in any one of them by selecting. So let's go with the second one, BJ Moose. And you'll notice that when I log in, if I click on the gear item, I have a choice of different desktops. Okay, here's the default on CentOS Stream, which is a Wayland, but I can pick a couple of different kinds of X11s if I want. I'll type in the password. And I log in. Depending on what's going on, I may see a little bit of information. And that's all that's involved in logging in. I probably won't see a hell of a lot. This is a new user without much going on. If I click on activities, for instance, I'll see some favorite applications. If I click on terminal here, I can bring up a terminal if I want to do command line activity. To log out, all I have to do is go in the upper right corner, and I can click on my name, and then I can say either switch user or log out. I would do switch user if I want to keep more than one session active at a time for different people, which is something you probably won't want to do very often, but it would mean if I came back into this user session, I would see the whatever applications I had open. But I'll just pick on log out, and then I click here, log out, and I'm back to my greeter or my login screen where I can pick the users again. So I can log in on any one of them. So that's a simple demonstration of how one logs in and out of a system.
Each Linux distribution comes with its own set of desktop backgrounds. You can change the default by choosing a new wallpaper or selecting a custom picture to be set as the desktop background. If you don't want to use an image as the background, you can select a color to be displayed on the desktop instead. In addition, you can also change the desktop theme, which changes the look and feel of the Linux system. The theme also defines the appearance of application windows. So let's see how to change the desktop background and theme.
We're going to demonstrate how to change the background wallpaper on a Red Hat 7 system. All recent Linux distributions have exactly the same method, so this will suffice to show for all. So all we have to do is click on the background with a right click and change background. Click on background again, and then we have a choice between wallpapers that the system knows already, and it's possible to load up other ones. So let's say we pick this one here, and you see now the background has been changed. Or I could pick, for instance, a picture stored on my machine in my pictures directory under my home directory. So I'll pick this one, and you see it's been changed. So that's all we have to do to change the background on any recent Linux system.
Most common settings, both personal and system-wide, are to be found by clicking in the upper right-hand corner on either a gear or other obvious icon, depending on your Linux distribution. However, there are many settings which many users would like to modify, which are not accessible in that way. The default settings utility is unfortunately rather limited in modern GNOME-based distributions. Unfortunately, the quest for simplicity has actually made it difficult to adapt your system to your tastes and needs. Fortunately, there is a standard utility, GNOME Tweaks, which exposes many more setting options. It also permits you to easily install extensions by external parties. Not all Linux distributions install this tool by default, but it's always available. You may have to run it by hitting Alt F2 and then typing in the name. You may want to add it to your favorites list, as we shall discuss. In this screenshot, the keyboard mapping is being adjusted so the useless caps lock key can be used as an additional control key. This saves users who use control a lot, such as Emacs aficionados, from getting physically damaged by pinky strain. The visual appearance of applications, the buttons, scroll bars, widgets, and other graphical components, are controlled by a theme. GNOME comes with a set of different themes which can change the way your applications look. The exact method for changing your theme may depend on your distribution. For older GNOME-based distributions, you can simply run GNOME tweaks, as shown in this screenshot from Ubuntu. However, now you'll be able to see a demonstration for logging in and out on the major Linux distribution families we'll concentrate on in this course. Note that evolution has brought us to a stage where it matters little which distribution you choose, as they're all rather similar.
Recent Linux distributions which use the GNOME desktop look remarkably the same when it comes to the process of starting up and shutting down. So we will demonstrate that here by using a VMware hypervisor on a Red Hat Enterprise Linux host, and we'll demonstrate 3 recent distributions and how they boot. So we've already teed them up. So here I will start CentOS 8 Stream. Here I will start Ubuntu 2004. And here I will start OpenSUSE Leap 15.3. So you'll see a little bit different messages on each as they boot according to how Grub is configured and what the possible kernel choices are. It will take longer to boot than they normally would if I was only doing one at a time, simply because the host machine is a little bit overloaded running 3 virtual machines. It really doesn't have a ton of memory. In this case, I have allotted 3 gigabytes of memory to each out of a total of 16 gigabytes on the machine, so it's a little bit memory stressed. So we'll just wait till they start and reach their greeter screen, which you see we've already done that on Ubuntu. We've already done that on OpenSUSE Leap, and it's taking somewhat longer on CentOS 8 Stream. So let's log into these guys while we wait for CentOS Stream to get ready. So I'll log in the student password here on the Ubuntu machine. I'll do the same thing on the OpenSUSE machine. And now we're just waiting for the CentOS 8 machine. Finally ready, and then I'll log in there as well. And you notice they have different background pictures just because we have selected different background pictures over time, but they all arrive to pretty much the same appearance with an activities and an applications menu, and then Ubuntu still likes to have this sidebar on the left with major applications. I can easily bring that up on the other ones. For instance, if I type activities here, activities on OpenSUSE, I will see the same thing there. And then the process of shutting down is also quite similar. All I need to do is click in the upper right hand corner and I find the power icon and I just say power off. I'll do the same thing with Ubuntu. I get power off and I go power off, and I can do the same thing with OpenSUSE. Power off and power off. And so it's remarkably the same from distribution to distribution these days.
It's often a good idea to lock your screen to prevent other people from accessing your session while you're away from your computer. Note, this does not suspend the computer. All your applications and processes continue to run while the screen is locked.
Let's show how to lock and unlock your screen on any recent GNOME distribution. So the simplest way is to go to the upper right corner and click and find the lock button. And simply click on that. And then you can unlock it by clicking on the display on the time there and just typing in the password again. Very simple. Another way to do it is through combination of keys. Depending on your machine, this will generally be the super key plus L or the super key plus the escape, where the super key is also known as the Windows key. So let me do that here. And once again, I brought up the lock window, and I can simply unlock it again. So that's all that's involved. It's very simple.
Linux is a true multi-user operating system, which allows more than one user to be simultaneously logged in. If more than one person uses the system, it's best for each person to have their own user account and password. This allows for individualized settings, home directories, and other files. Users can take turns using the machine, while keeping everyone's sessions alive, or even be logged in simultaneously through the network.
Let us demonstrate how to switch users on an Ubuntu machine with several accounts. So first, I will choose the Linux Foundation student as the account to log into. Type my password and sign in. And then if I look in the upper right-hand corner and click there, I will see LF student, and I can click on either log out or switch user. Notice if I log out, I really log out, but if I switch user, I will just lock the user account, and then when I start up, I will preserve all of my sessions and open windows, etc. when I restart. On some distributions, you may actually see a list of users at this screen, but not on Ubuntu. So I'll say switch user. I'm back to the greeter screen. And let me pick the second one, Theodore Cleaver. And log in as that other user. And there we go. And now if I look up here again, I can do the same thing. So let me click on the name and I'll say switch user. And if I pick student again, you notice here it says unlock and not restart. That means that if I were to log in now, I will have preserved all the open windows and running applications from before. This will look the same essentially on all Linux distributions of recent vintage. So it's very easy to switch users and not lose any information from what you're already doing.
Besides normal daily starting and stopping of the computer, a system restart may be required as part of certain major system updates, generally only those involving installing a new Linux kernel. Initiating the shutdown process from the graphical desktop is rather trivial on most current Linux distributions, with very little variation. We'll discuss later how to do this from the command line using the shutdown command. In all cases, you click on either a settings or gear or a power icon and follow the prompts. To shut down the computer on any recent GNOME-based Linux distribution, perform the following steps. First, click the power or the gear icon in the upper right-hand corner of the screen. Second, click on the power off, restart, or cancel. If you do nothing, the system will shut down in 60 seconds. Shutdown, reboot, and logout operations will ask for confirmation before going ahead. This is because many applications will not save their data properly when terminated this way. Always save your documents and data before restarting, shutting down, or logging out. All modern computers support suspend or sleep mode when you want to stop using your computer for a while. Suspend mode saves the current system state and allows you to resume your session more quickly while remaining on, but uses very little power in the sleeping state. It works by keeping your system's applications, desktop, and so on in system RAM, but turning off all the other hardware. This shortens the time for a full system startup, as well as conserves battery power. Want to note that modern Linux distributions actually boot so fast that the amount of time saved is often minor. Even experienced users can forget the precise command that launches an application, or exactly what options and arguments it requires. Fortunately, Linux allows you to quickly open applications using the graphical interface. Applications are found at different places in Linux and within GNOME. They can be found from the Applications menu in the upper left-hand corner, or from the Activities menu in the upper left-hand corner. Also, in some Ubuntu versions, from the dash button in the upper left-hand corner. For KDE and some other environments, applications can be opened from the button in the lower left-hand corner. In the upcoming sections, you will learn how to perform basic Linux operations using the graphical interface. Unlike other operating systems, the initial install of Linux usually comes with a wide range of applications and software archives that contain thousands of programs that enable you to accomplish a wide variety of tasks with your computer. For most key tasks, a default application is usually already installed. However, you can always install more applications and try different options. For example, Firefox is popular as the default browser in many Linux distributions, while Epiphany, Conqueror, and Chromium, the open source of Google Chrome, are usually available for install from software repositories. Proprietary web browsers such as Opera and Chrome are also available. Locating applications from the GNOME and KDE menus is easy, as they are neatly organized in functional submenus. Multiple applications are available to accomplish various tasks and to open a file of a given type. For example, you can click on a web address while reading an email and launch a browser such as Firefox or Chrome. To set the default applications, enter the Settings menu on all recent Linux distributions and then click on either Default Applications or Details Default Applications.
Let's now demonstrate how to set default applications on a Red Hat system. We go to the upper right hand corner, click on the top bar, then scroll down to the gears icon for settings, go down to the bottom for details, and then I can click on default applications. So you see under web or browser, there are three choices on this system. I have Google Chrome, Firefox, or Opera. We'll leave it at Google Chrome. For video, the default choice is Videos, which is actually a program called Totem, but let's switch it to the VLC Media Player. And for the image viewer, I have the built-in image viewer, or I could switch to the GNU image manipulation program, better known as GIMP. So, on all recent distributions with a GNOME desktop, the procedure is identical and absolutely the same, and it's very simple to change your default applications.
Each distribution implements the Nautilus or File Manager utility, which is used to navigate the file system. It can locate files, and when a file is clicked upon, either it will run if it's a program, or an associated application will be launched using the file as data. This behavior is completely familiar to anyone who has used other operating systems. To start the File Manager, you will have to click on its icon, a file cabinet, which is easily found, usually under Favorites or Accessories. It will have the name Files. This will open a window with your home directory displayed. The left panel of the File Manager window holds a list of commonly used directories, such as Desktop, Documents, Downloads, and Pictures. The File Manager lets you access different locations on your computer and the network, including the home directory, the desktop, documents, pictures, and other locations. Every user with an account on the system will have a home directory, usually created under home/home, and usually named according to the user, such as /home/student. By default, files the user saves will be placed in a directory tree starting there. Account creation, whether during system installation or at a later time, when a new user is added, also induces default directories to be created under the user's home directory, such as Documents, Desktop, and Downloads. The File Manager allows you to view files and directories in more than one way. You can switch between the icons and list formats, either by clicking the familiar icons in the top bar, or you can press Ctrl 1 or Ctrl 2 respectively. In addition, you can also arrange the files and directories by name, size, type, or modification date for future sorting. To do so, click View and select Arrange Items. Another useful option is to show hidden files, sometimes imprecisely called system files, which are usually configuration files that are hidden by default and whose name starts with a dot. To show hidden files, select Show Hidden Files from the menu or press Ctrl-H. The file browser provides multiple ways to customize your window view to facilitate easy drag-and-drop file operations. You can also alter the size of the icons by selecting Zoom In and Zoom Out under the View menu. The File Manager includes a great search tool inside the file browser window. 1. Click Search in the toolbar to bring up a text box. Then enter the keyword in this text box. This causes the system to perform a recursive search from the current directory for any file or directory which contains a part of this keyword. You can refine your search beyond the initial keyword by providing drop-down menus to further filter the search. Deleting a file in Nautilus will automatically move the deleted file to the .local/share/trash/files directory, basically a trash can, under the user's home directory. There are several ways to delete files and directories under Nautilus. 1. You select all the files and directories that you want to delete. Then press Ctrl-Delete on your keyboard or right-click the file. Then select Move to Trash. Note that you may have a Delete Permanently option, which bypasses the trash folder, and this option may be visible all the time or only in list rather than icon mode. To permanently delete a file, on the left panel inside a Nautilus file browser window, right-click on the trash, on the trash directory. Select Empty Trash, and that's all. Alternatively, select the file or directory you want to permanently delete and press Shift-Delete.
Let's see how to locate the Firefox application in Locate Firefox. Click Activities on the top left corner of your desktop. On the left panel, click the Show Applications icon. Click the Firefox icon. Close Firefox by clicking Close in the top right corner of the Firefox window. Next, let's explore the home directory using the File Manager. Try to view files in list mode, create a new empty document, save it, and remove it. Click Activities in the upper left corner of your desktop. In the left panel, click the File Manager icon. This will, by default, open the home directory. To view files in list mode, click the List icon in the upper right of the File Manager window. Double-click the document directory to open it. Click Activities in the top left corner of your desktop to launch gedit. Type gedit in the search box. Click the gedit icon to open it. Type your name and click Close in the top right corner of the gedit window to create and close a file. Click Save As to save the created file. Select Documents from the left panel of the Save As window. Type Test to save the file by that name. Click Save to save the file and close gedit. This brings you back to the document directory. Right-click the test file in the document window. Select Move to Trash to remove the file.
You have completed Chapter 4. Let's summarize the key concepts covered. GNOME is a popular desktop environment and graphical user interface that runs on top of the Linux operating system. The default display manager for GNOME is called GDM. The GDM display manager presents the user with the login screen, which prompts for the user the login username and password. Logging out through the desktop environment kills all processes in your current X session and returns to the display manager login screen. Linux enables users to switch between logged in sessions. Suspending puts the computer into sleep mode. For each key task, there is generally a default application installed. Every user created in the system will have a home directory. The Places menu contains entries that allow you to access different parts of the computer and the network. Nautilus gives 3 formats to view files: Each Linux distribution comes with its own set of desktop backgrounds. GNOME comes with a set of different themes, which can change the way your applications look. By the end of this chapter, you should be able to apply system display and date and time settings using the System Settings panel, track the network settings and manage connections using the Network Manager in Linux, install and update software in Linux from a graphical interface. Note that we'll revisit all these tasks later when we discuss how to accomplish them from the command line. The System Settings panel allows you to control most of the basic configuration options and desktop settings, such as specifying the screen resolution, managing network connections, or changing the date and time of the system. For the GNOME Desktop Manager, one clicks on the upper right-hand corner and then selects the Tools image, the screwdriver crossed with a wrench or a gear. Depending on your distribution, you may find other ways to get into the settings configurations as well. You'll also find variations in the menu layout between Linux distributions and versions, so you may have to hunt for the settings you need or to examine or modify. To get deeper into configuration, one can click on the devices on the previous menu in order to configure items like the display, the keyboard, the printers, etc. One can also click on the users icon, which may be under details, to set values for system users, such as their login picture, password, etc. A lot of personalized configuration settings do not appear on the settings menu. Instead, you have to launch a tool called either GNOME Tweaks or GNOME Tweak Tool. We have not really discussed working at the command line yet, but you can always launch a program such as this by doing Alt F2 and typing in the command. Some distributions have a link to the Tweaks menu in the settings, but for some mysterious reason, many obscure this tool's existence, and it becomes hard to discover how to modify even rather basic desktop attributes and behaviors. Important things you can do with this tool include selecting a theme, configuring extensions, which you can get from your distribution or download from the internet. You can control fonts, modify the keyboard layout, and set which programs start when you log in. The most recent GNOME versions have removed a lot of the functionality of GNOME Tweaks. Extensions now have to be configured using a new app called GNOME Extensions app. The reasoning for this is obscure. Here you can see a screenshot from a Red Hat system with quite a few extensions installed, but not all being used. Clicking on Settings Displays or Settings Devices Displays will expose the most common settings for changing the desktop appearance. These settings function independently of the specific display drivers you're running. The exact appearance will depend enormously on how many monitors you have and other factors, such as Linux distribution and particular version. If your system uses a proprietary video card driver, usually from NVIDIA or AMD, you'll probably have a separate configuration program for that driver. This program may give more configuration options, but may also be more complicated and might require sysadmin root access. If possible, you should configure the settings in the Displays panel rather than with the proprietary program. The X server, which actually provides the GUI, uses /etc/x11/xorg.conf as its configuration file, if it exists. In modern Linux distributions, this file is usually present only in unusual circumstances, such as when certain less common graphic drivers are in use. Changing this configuration file directly is usually for more advanced users. While your system will usually figure out the best resolution for your screen automatically, it may get this wrong in some cases, or you might want to change the resolution to meet your needs. You can accomplish this using the Displays panel. The switch to the new resolution will be effective when you click Apply, and then confirm that the resolution is working. In case the selected resolution fails to work or you're just not happy with the appearance, the system will switch back to the original resolution after a short timeout. Once again, the exact appearance of the configuration screen will vary a lot between distributions and versions, but usually it's rather intuitive and easy once you find the configuration menus. In most cases, the configuration for multiple displays is set up automatically as one big screen spanning all monitors, using a reasonable guess for screen layout. If the screen layout is not as desired, a checkbox can turn on mirrored mode, where the same display is seen on all monitors. Clicking on a particular monitor image lets you configure the resolution of each one and whether they make one big screen or mirror the same video.
Configuring display settings such as resolution is almost identical on all major distributions. So we'll demonstrate that running virtual machines under VMware on a Red Hat 8 host. So let's begin with showing what it looks like on Ubuntu. So I go up in the upper right hand corner and I find the settings button. And then in the main panel here, we have displays, so we've already clicked on that. And you see the easiest thing to do here is I can change the resolution to be any one of these numbers. Now, you can continuously vary the display size usually on a virtual machine, and by dragging and dropping the corners, you see now it's changed to another number. But that's all that's involved in Ubuntu, for instance. If I want to go to open, well, let's try CentOS. In CentOS 8 Stream, actually, I find the settings once again. And then here, I have to scroll down to Devices, and then Displays is in there, and we have the identical setup except for this night light option, which is for looking in a darker situation, which we also had in the Ubuntu, is just located in a different place. On OpenSUSE, you'll see it's virtually identical as well. I just click on the settings gear button here. And once again, I have to go to devices like I did on the Red Hat system. And I have the identical situation. You couldn't tell what operating system you were on if you just looked at this. Now, these are all virtual machines with one terminal. If I look on the host, which actually has 3 different monitors hooked up to it, you'll see then I get something like this, where I can see all 3 of my monitors. I configure any one of them. Here it's doing the smaller one, the 18-inch one, but I could switch to the 27 or the 24, and I can control their different resolutions. If I move these guys around here, I can change the way the 3 of them are laid out from left to right. I don't particularly want to do that because it gets kind of messy, but this is how you can control which one's in the middle, which is on the right or the left, etc. So these days, configuring the display resolution and some other basic things is really very simple, very intuitive. The hardest thing is just to find the settings icon to click on.
By default, Linux always uses coordinated universal time for its own internal timekeeping. Displayed or stored time values rely on the system time zone setting to get the proper time. UTC is similar to, but more accurate than, Greenwich Mean Time. If you click on the time displayed on the top panel, you can adjust the format with which the date and time is shown. On some distributions, you can also alter the values. The more detailed date and time settings can be selected from the Date and Time window in the System Settings menu. The automatic settings are referring to the use of Network Time Protocol, which we'll discuss next. The Network Time Protocol is the most popular and reliable protocol for setting the local time by consulting established internet servers. Linux distributions always come with a working NTP setup, which refers to a specific time servers run or relied on by the distribution. This means that no setup beyond on or off is generally required for network time synchronization. All Linux distributions have network configuration files, but file formats and locations can differ from one distribution to another. Hand editing of these files can handle quite complicated setups, but it's not very dynamic or easy to learn and use. Network Manager was developed to make things easier and more uniform across distributions. It can list all available networks, both wired and wireless, allow the choice of a wired, wireless, or mobile broadband network, handle passwords, and set up virtual private networks. Except for unusual situations, it's generally best to let Network Manager establish your connections and keep track of your settings. In this section, you'll learn how to manage network connections, including wired and wireless connections, and mobile broadband and VPN connections. Wired connections usually do not require complicated or manual configuration. The hardware interface and signal presence are automatically detected, and then Network Manager sets the actual network settings via Dynamic Host Configuration Protocol, or DHCP. For static configurations that do not use DHCP, manual setup can also be done easily through Network Manager. You can also change the Ethernet MAC address, or Media Access Control address, if your hardware supports it. The MAC address is a unique hexadecimal number of your network card. Wireless networks are usually not connected by default. You can view the list of available wireless networks and see which one, if any, you're currently connected to by using Network Manager. You can then add, edit, or remove known wireless networks, and also specify which ones you want connected by default when present. To configure a wireless network in any recent GNOME-based distribution, click on the upper right corner of the top panel, which brings up a Settings and/or Network window. While the exact appearance will depend on Linux distribution and version, it will always be possible to click on a Wi-Fi submenu as long as the hardware is present. Here is an example from a RHEL 8 system. Select the wireless network you wish to connect to. If it's a secure network, the first time it will request that you enter the appropriate password. By default, the password will be saved for subsequent connections. If you click on Wi-Fi settings, you will bring up this. If you click on the gear icon for any connection, you can configure it in more detail. Older and other Linux distributions may look quite a bit different in detail, but the steps and choices are essentially identical, as they're all running Network Manager with perhaps somewhat different clothing.
Let's demonstrate how to control wired and wireless network connections on a Red Hat system. If I click on the upper right hand corner, for instance, if I want to look at the wired connection, I can just scroll down to the wired connection, and then wired settings, and it asks me for my password, the root password, because it wants to have a super user only control network connections. And you'll see I have a 1000 megabit connection. If I click on the gear icon, I can control the settings. On the details first screen, it says it connects automatically when the system starts and all users can use it. On identity, I give what the name of the interface looks like, not the name of the system. In older systems that would have been ETH0, ETH1, etc., but as we will discuss later, newer systems have these more complex names. Under IPv4, we control the basic Internet Protocol systems settings. Most of the time, you'll leave it alone at automatic DHCP, Dynamic Host Configuration Protocol, where the system figures out its address from the server, etc. If you understand how the importance of manual settings, you can specify an address, a net mask, a gateway, you can select a particular DNS server, and you can specify routes to certain addresses. If you understand those concepts, this is where you would go to control all that. We're not changing anything, so I'll just hit cancel. Now, if I want to control Wi-Fi settings, I could go back to that upper right corner, or I can just click on the Wi-Fi setting here, and once again, it's asking me for the super user password. These are the different wireless networks that are available at the moment. They all have locks next to them, means They require a password. This is the one that I'm actually on, CoopJ, the first one. And if I click on the settings there, once again, it's going to ask me for my super user password. And I see essentially the exact same settings I had on the wired connection. The automatic startup, as other people use it, the identity, and whether I want to use DHCP or set things manually or not. So that's all there really is in the graphical interface to control basic network connections. It's rather simple, and it looks the same on all recent Linux distributions.
You can set up mobile broadband connection with Network Manager, which will launch a wizard to set up the connection details for each connection. Once the configuration is done, the network is configured automatically each time the broadband network is attached. Network Manager can also manage your VPN connections. It supports many VPN technologies, such as native IPsec, Cisco, OpenConnect, via either the Cisco client or a native open source client, Microsoft PPTP, and OpenVPN. You might get support for VPN as a separate package from your distributor. You need to install this package if your preferred VPN is not supported. Each package in Linux distribution provides one piece of the system, such as the Linux kernel, the C compiler, utilities for manipulating text or configuring the network, or for your favorite web browsers and email clients. Packages often depend on each other. For example, because your email client communicates using SSL/TLS, it will depend on a package which provides the ability to encrypt and decrypt SSL and TLS communication, and will not install unless that package is also installed at the same time. All systems have a lower level utility which handles the details of unpacking a package and putting the pieces in the right places. Most of the time you will be working with a higher level utility which knows how to download packages from the internet and can manage dependencies and groups for you. In this section, you will learn how to install and update software in Linux using the Debian packaging system, used by systems such as Ubuntu as well, and RPM packaging systems, which is used by both Red Hat and the SUSE family systems. These are the main ones in use, although there are other ones which work well for other distributions, which are less used. Let's look at the package management for the Debian family system. DPKG is the underlying package manager for these systems. It can install, remove, and build packages. Unlike higher level packages management systems, it does not automatically download and install packages and satisfy their dependencies. For Debian-based systems, the higher level package management system is the Advanced Package Tool, or APT, system of utilities. Generally, while each distribution within the Debian family uses APT, it creates its own user interface on top of it. For example, apt-get or apt-get, Symptatic, Ubuntu Software Center, etc. Although apt repositories are generally compatible with each other, the software they contain generally is not. Therefore, most repositories target a particular distribution, like Ubuntu, and often software distributors ship with multiple repositories to support multiple distributions. Demonstrations are shown later in this section. Red Hat Package Manager, or RPM, is the other package management system popular on Linux distributions. It was developed by Red Hat and adopted by a number of other distributions, including SUSE and OpenSUSE, CentOS, Oracle Linux, and others. The high-level package manager differs between distributions. Red Hat family distributions historically use RHEL or CentOS, and Fedora uses DNF, while retaining good backward compatibility with the older Yum program. SUSE family distributions, such as OpenSUSE, also use RPM, but use the zipper interface. The Yet Another Setup Tool, or YAST, software manager is similar to other graphical package managers. It's an RPM-based application. You can add, remove, or update packages using this application very easily. To access the YAST software manager, first click Activities, then in the search box type YAST, and click on the YAST icon. Then click Software Management. You can also find YAST by clicking on Applications, Other YAST, which is a strange place to put it, but OpenSUSE's YAST software management application is similar to the graphical package managers in other distributions. A demonstration of the YAST software manager is seen later in this section.
We are now going to demonstrate software package management from a graphical interface using the OpenSUSE Linux distribution. The tool we want to use for doing this is YAST, Y-A-S-T, and there's two different ways I can reach it. If I have the GNOME shell extension installed, which shows the applications menu, which doesn't come by default, I can go down to Systems Tools and then go down to YAST. Or I can always go up to the upper right hand corner, click on the tool icon, and then at the bottom here on the system, click on YAST. It will want the root password because I'm going to manipulate what's installed on the system. And so if I go to Software, I can go to Software Management. Now the first thing that YAST has to do is study the system and get a database of every possible package. So you can look at the packages on the system in different ways. You can look by what's called RPM groups. So here's all the games are grouped under amusements. I have applications, development, and all different kinds of development subcategories, tools, documentation, etc. Or RPM groups. That is RPM groups. Okay. Yeah, or I can look at package groups, which maybe is a little more intuitive. So I could click on, let's say, multimedia and see all the different programs that are involved in dealing with multimedia. Suppose I want to install something or inquire as to where something is installed. I can click on Search and type something in here. I'll type GNU plot. And I bring up quickly all the different GNU plot programs there are. The main one you see has a check mark in the box. That means it's already installed. I will decide to install GNU plot doc, which is a small documentation package. And then in order to do the install, I will click on Accept. And it will go ahead and do it. It's a pretty small package. It doesn't take long. If it needed some other packages to function, it would have installed them at the same time. So now I'll say Continue. And if I want to remove it because I don't really need it, I'll type that in the search again. And then I click on here until I get an X for removal. And then I say Accept. And it's removing it. So that's all I had to do some basic package installation and removal under GNOME software with OpenSUSE. Pretty simple. Experienced Linux administrators probably do most of their package management from the command line rather than from a graphical interface. However, every Linux distribution has at least one graphical interface for installing, upgrading, removing, etc. various software packages. So let's take a look at a recent Ubuntu system. I can go to Applications and then down to System Tools. And first let's look at the one at the bottom here, which just says Software. This is actually a program called GNOME Software. You can always install it if it hasn't been installed on your system. It looks somewhat like an App Store or a Play Store from Android. And it's pretty obvious. You can click on any one of these to try to install, etc. And at the bottom, you'll see things are grouped by category. So for instance, I could click on utilities, and then I'll see a bunch of different utilities that may or may not be installed on your system already. Okay. Or I could search for various things. So let me go back to the main page, and if I click on the hourglass up in the corner here, I can search. So let's say I search on terminal. You'll see it'll come up with a number of different things I could install. You'll see here, this terminal here is the GNOME terminal, and it says installed in a rather small font here. And if I wanted to install something else, I could just say, for instance here, I could click on that and I would say install, and it could just be installed. Or if I want something a little more fun, let's say I'll look for a program called Cheese, which lets you use your webcam to take pictures or make videos, etc. And I can say remove, because it turns out it's already installed. So let me remove it. And it's going to want a password to do this, which shouldn't be that surprising. So I type my password and it's removing it. And then, if I want to reinstall it, which I'll do, I'll just say install and give the password again. So this is not a very complex program to use. It's pretty easy to use GNOME software. And you notice at the top you have a list here of Explore, which is where you are now. Installed would be all your installed packages. And if you do updates, it's telling me the system has 2 sets of updates that I really should install, but to save time, I won't do that right now. So that's one graphical interface. There's a much older graphical interface that's available in Ubuntu called Synaptic. So let's do that one. I thought it was, it's under System Tools. There we go. Synaptic Package Manager. And once again, this is going to ask for a password. And it's just an informatory message. And this is actually a very simple, easy to use, and gives you a clearer vision of exactly where everything came from compared to the more modern graphical interfaces. It's pretty straightforward to use. It's organized by either sections here. I can do it in other ways. I can do searching, etc. So suppose I want to search, well, I'll do the same search here, terminal. And it's going to show me all the packages that either have terminal in the name or discuss terminal. If I want to restrict it to ones that have only in the name, I can do that. And it's pretty straightforward to use. I won't run through this. These are already installed because they're in green. I can install any of these other ones, and I can just click on that, and then let's say I want to do Qt terminal. I would say mark for installation. And it says in order to this to work, it has to install these other packages too, which it depends on. So we won't bother to do that. And that's briefly what you can do on an Ubuntu system with a graphical software package installations and removals.
You have completed Chapter 5. So let's summarize the key concepts covered. You can control basic configuration options and desktop settings through the System Settings panel. Linux always uses Coordinated Universal Time, or UTC, for its own internal timekeeping. You can set the date and time settings from the System Settings window. The Network Time Protocol is the most popular and reliable protocol for setting the local time via internet servers. The Displays panel allows you to change the resolution of your display and configure multiple screens. The Network Manager can present available wireless networks. It allows the choice of a wireless or mobile broadband network, handles passwords, and sets up VPNs. The DPKG and RPM are the most popular package management systems used on Linux distributions. Debian distributions use DPKG and apt-based utilities for package management. RPM was developed by Red Hat and adopted by a number of other distributions, including OpenSUSE, CentOS, Oracle Linux, and others. By the end of this chapter, you should be familiar with common Linux applications, including Internet applications such as browsers and email programs, Office productivity suites such as LibreOffice, developer tools such as compilers, debuggers, etc., multimedia applications such as those for audio and video, graphic editors such as the GIMP and other graphics utilities. The Internet is a global network that allows users around the world to perform multiple tasks, such as searching for data, communicating through emails, and online shopping. Obviously, you need to use network-aware applications to take advantage of the Internet. These include web browsers, email clients, streaming media applications, Internet relay chats, and conferencing software. As discussed in the graphical interface chapter, Linux offers a wide variety of web browsers, both graphical and text-based, including Firefox, Google Chrome, Chromium, Epiphany, renamed Web, Konqueror, Lynx, Lynx W3M, and Opera. Email applications allow for sending, receiving, and reading messages over the Internet. Linux systems offer a wide number of email clients, both graphical and text-based. In addition, many users simply use their browsers to access their email accounts. Most email clients use the Internet Message Access Protocol, or IMAP, or the older POP, Post Office Protocol, to access email stored on a remote mail server. Most email applications also display HTML formatted emails that include objects like pictures and hyperlinks. Linux supports the following types of email applications: graphical email clients such as Thunderbird, Evolution, and Clausemail, text mode email clients such as Mutt and Mail, all web browser based clients such as Gmail, Yahoo Mail, and Office 365. Linux systems provide many other applications for performing Internet-related tasks. These include FileZilla, Pidgin, Ikaga, and HexChat. Most day-to-day computer systems have productivity applications, sometimes called office suites, available or installed. Each suite is a collection of closely coupled programs used to create and edit different types of files, such as text, spreadsheets, presentations, graphical objects. Most Linux distributions offer LibreOffice, an open source office suite that started in 2010 and has evolved from OpenOffice. While other office suites are available, as we have listed, LibreOffice is the most mature, and it's also the most widely used and intensely developed. In addition, Linux users have full access to Internet-based office suites such as Google Docs and Microsoft Office 365. The component applications included in LibreOffice are Writer for word processing, Calc for spreadsheets, Impress for presentations, Draw for creating and editing graphics and diagrams. The LibreOffice applications can read and write non-native document formats, such as those used by Microsoft Office. Usually, fidelity is maintained quite well, but complicated documents might have some imperfect conversions. Linux distributions come with a complete set of applications and tools that are needed by those developing or maintaining both user applications and the kernel itself. These tools are tightly integrated and include advanced editors customized for programmers' needs, such as V and Emacs, compilers for every computer language that has ever existed, including very popular new ones such as Golang and Rust, debuggers such as GDB, and various graphical front ends to it, and many other debugging tools, performance measuring and monitoring programs, some with easy to use graphical interfaces, others more arcane and meant to be used only by serious, experienced development engineers. Complete integrated development environments, or IDEs, such as Eclipse and Visual Studio Code, that put all these tools together. On other operating systems, these tools have to be obtained and installed separately, often at a high cost, while on Linux they are all available at no cost through standard package installation systems. Multimedia applications are used to listen to music, watch videos, etc., as well as to present and view text and graphics. Linux systems offer a number of sound player applications, including Amarok, Audacity, and Rhythmbox. Of course, Linux systems can also connect with commercial online music streaming services, such as Pandora and Spotify, through web browsers. Movie and video players can portray input from many different sources, either local to the machine or on the internet. Linux systems offer a number of movie players, including VLC, MPlayer, Zine, Totem. Movie editors are used to edit videos or movies. Linux systems offer a number of movie editors, including Cinepaint, Blender, Cinelera, and FFmpeg. Graphic editors allow you to create, edit, view, and organize images of various formats. The New Image Manipulation Program, or GIMP, is a feature-rich image retouching and editing tool similar to Adobe Photoshop, and it's available on all Linux distributions. Some features of GIMP are: it can handle any image format, it has many special purpose plugins and filters, it provides extensive information about the image, such as layers, channels, and histograms. In addition to GIMP, there are other graphics utilities that help perform various image-related tasks, including eog, Inkscape, Convert, and Scribus. You have completed Chapter 6. Let's summarize the key concepts covered. Linux offers a wide variety of internet applications, such as web browsers, email clients, online media applications, and others. Web browsers supported by Linux can be either graphical or text-based, such as Firefox, Google, Chrome, Epiphany, W3M, Lynx, and others. Linux supports graphical email clients, such as Thunderbird, Evolution, and Clausmail, and text mode email clients, such as Mutt and Mail. Linux systems provide many other applications for performing internet-related tasks, such as FileZilla, XChat, Pidgin, and others. Most Linux distributions offer LibreOffice to create and edit different kinds of documents. Linux systems offer entire suites of development applications and tools, including compilers and debuggers. Linux systems offer a number of sound players, including Amarok, Audacity, and Rhythmbox. Linux systems offer a number of movie players, including VLC, MPlayer, Zine, and Totem. Linux systems offer a number of movie editors, including Kino, Cinepaint, Blender, among others. The GIMP utility is a feature-rich image retouching and editing tool available on all Linux distributions. Other graphics utilities that help perform various image-related tasks are eog, Inkscape, Convert, and Scribus. By the end of this chapter, you should be able to use the command line to perform operations in Linux, search for files, create and manage files, install and update software. Linux system administrators spend a significant amount of their time at a command line prompt. They often automate and troubleshoot tasks in this text environment. There's a saying: graphical user interfaces make easy tasks easier, while command line interfaces make difficult tasks possible. Linux relies heavily on the abundance of command line tools. The command line interface provides the following advantages. No GUI overhead is incurred. Virtually any and every task can be accomplished while sitting at the command line. You can implement scripts for often used or easy to forget tasks and series of procedures. You can sign into remote machines anywhere on the internet. You can initiate graphical applications directly from the command line instead of hunting through menus. While graphical tools may vary among Linux distributions, the command line interface does not. A terminal emulator program emulates or simulates a standalone terminal within a window on the desktop. By this we mean it behaves essentially as if you were logging into the machine at a pure text terminal with no running graphical interface. Most terminal emulators programs support multiple terminal sessions by opening additional tabs or windows. By default on GNOME desktop environments, the GNOME Terminal application is used to emulate a text mode terminal in a window. Other available terminal programs include Xterm, Console, default on KDE, and Terminator. To open a terminal on any system using a recent GNOME desktop, click on Applications, System Tools, Terminal, or Applications, Utilities, Terminal. If you do not have the Applications menu, you will have to install the appropriate GNOME Shell extension package and turn it on with GNOME tweaks. On any but some of the most recent GNOME-based distributions, you can always open a terminal by right-clicking anywhere on the desktop background and selecting Open in Terminal. If this does not work, you will once again need to install and activate the appropriate GNOME Shell package. You can also hit Alt F2 and type in either GNOME Terminal or Console, whichever is appropriate. Because distributions have had a history of bearing opening up a command line terminal, and the place in menus may vary in the desktop GUI, it is a good idea to figure out how to pin the terminal icon to the panel, which might mean adding it to the favorites grouping on GNOME systems. There are some basic command line utilities that are used constantly, and it would be impossible to proceed further without using some of them in simple forms before we discuss them in more detail. A short list has to include cat, used to type out a file or combine files, head, used to show the first few lines of a file, tail, used to show the last few lines of a file, man, used to view documentation. This screenshot shows elementary uses of these programs. Note the use of the pipe symbol, the vertical line, used to have one program take as input the output of another. For the most part, we will only use these utilities in screenshots displaying various activities before we discuss them in detail. Most input lines entered at the shell prompt have three basic elements: the command, the options, and the arguments. The command is the name of the program you are executing. It may be followed by one or more options, or switches, that modify what the command may do. Options usually start with one or two dashes, for example -p or --print, in order to differentiate them from arguments, which represent what the command operates on. However, plenty of commands have no options, no arguments, or neither. In addition, other elements, such as setting environment variables, can also appear on the command line when launching a task. All the demonstrations created have a user configured with sudo capabilities to provide the user with administrative privileges when required. Sudo allows users to run programs using the security privileges of another user, generally root, the superuser. On your own systems, you may need to set up and enable sudo to work correctly. To do this, you need to follow some steps that will not explain in much detail now, but you will learn about later in this course. When running on Ubuntu and some other recent distributions, sudo is already always set up for you during installation. On other Linux distributions, you will likely need to set up sudo to work properly for you after the initial installation. Next, you will learn the steps to set up and run sudo on your system. If your system does not already have sudo set up and enabled, you need to do the following steps. You will need to make modifications to the administrative or superuser root. While sudo will become the preferred method of doing this, we do not have to have it set up yet, so we will use su, which we'll discuss later in detail, instead. At the command line prompt, type su and press enter. You'll then be prompted for the root password, so enter it and press enter. You'll notice that nothing is printed. This is so others cannot see the password on the screen. You should end up with a different looking prompt, often ending with a hash mark or a pound sign. For example, su and then password. Now you need to create a configuration file to enable your user account to use sudo. Typically this file is created in the /etc/sudoers.d/directory with the name of the file as the same as your username. For example, for this demo, let's say your username is student. After doing step 1, you would then create the configuration file for student by doing this. Echo student all equals all. And then the directory here. Finally, some Linux distributions will complain if you do not also change permissions on the file by doing chmod 440 and then put the file name. That should be it. For the rest of this course, if you use sudo, you should be properly set up. When using sudo, by default, you will be prompted to give a password, your own user password, at least the first time you do it, within a specified time interval. It's possible, though very insecure, to configure sudo to not require a password, or change the time window in which the password does not have to be repeated with every sudo command. The customizable nature of Linux allows you to drop the graphical interface, temporarily or permanently, or to start it up after the system has been running. Most Linux distributions give an option during installation, or have more than one version of the install media, to choose between desktop, with a graphical desktop, and server, usually without one. Linux production servers are usually installed without the GUI, and even if it is installed, usually do not launch it during the system startup. Removing the graphical interface from a production server can be very helpful in maintaining a lean system, which can be easier to support and keep secure. VT, or virtual terminals, are console sessions that use the entire display and keyboard outside of a graphical environment. Such terminals are considered virtual because, although there can be multiple active terminals, only one terminal remains visible at a time. A VT is not quite the same as a command line terminal window. You can have many of those visible at once on a graphical desktop. One virtual terminal, usually number 1 or 7, is reserved for the graphical environment, and text logins are enabled on the unused VTs. Ubuntu uses VT7, but CentOS and RHEL and OpenSUSE use VT1 for the graphical display. An example of a situation where using VTs is helpful is when you run into problems with the graphical desktop. In this situation, you can switch to one of the text VTs and troubleshoot. To switch between VTs, press Ctrl-Alt function key for the VT. For example, press Ctrl-Alt-F6 for VT6. Actually, you only have to press the Alt-F6 key combination if you are in a VT and want to switch to another VT. Linux distributions can start and stop the graphical desktop in various ways. The exact method differs from distribution and among distribution versions. For the newer systemd-based distributions, the display manager is run as a service. You can stop the GUI desktop with the system control utility, and most distributions will also work with the teleinit command, as in sudo systemcontrol stop gdm or sudo teleinit 3. And restart it after logging into the console with sudo system control start gdm or sudo sudo telnet5. On Ubuntu versions before 18.04 LTS, substitute lightdm for gdm. In this section, we will discuss how to accomplish basic operations from the command line. These include how to log in and log out from the system, restart or shut down the system, locate applications, access directories, identify absolute and relative paths, and explore the file system. An available text terminal will prompt for a username with the string login and password. When typing your password, nothing is displayed on the terminal, not even an asterisk to indicate that you typed in something. And this is to prevent others from seeing your password. After you've logged into the system, you can perform basic operations. Once your session is started, either by logging into a text terminal or via a graphical terminal program, you can also connect and log into remote systems by using SSH. For example, by typing SSH student at remoteserver.com, SSH would connect securely to the remote machine, or remoteserver.com, and give student, that's the user, a command line terminal window, either using a password, as with regular logins, or a cryptographic key to sign in without providing a password to verify the identity. The preferred method to shut down or reboot the system is to use the shutdown command. This sends a warning message and then prevents further users from logging in. The init process will then control shutting down or rebooting the system. It's important to always shut down properly. Failure to do so can result in damage to the system and/or loss of data. The halt and power off commands issue shutdown-H to halt the system. Reboot issues shutdown-R and causes the machine to reboot instead of just shutting down. Both rebooting and shutting down from the command line requires superuser or root access. When administering a multi-user system, you have the option of notifying all users prior to shutdown, as in sudo shutdown-H 10 o'clock, shutting down for scheduled maintenance. Depending on the specifics of your particular distribution's policy, programs, and software packages can be installed in various directories. In general, executable programs and scripts should live in the /bin or /user/bin or /sbin or /user/sbin directories, or somewhere under /opt. They can also appear in the /user/local/bin or /user/local/sbin, or in a directory in a user's account space, such as /home/student/bin. One way to locate programs is to employ the which utility. For example, to find out exactly where the diff program resides on the file system, you can do which diff /user/bin/diff. If which does not find the program, where is a good alternative because it looks for packages in a broader range of system directories. So, where is diff? When you first log into a system or open a terminal, the default directory should be your home directory. You can print the exact path of this by typing echo home. Many Linux distributions actually open new graphical terminals in the $home/desktop. The following commands are useful for directory navigation.
Let's get some practice navigating among directories at the command line. So suppose I go to the temp directory, cd/tmp. I do pwd for print working directory, I'm at tmp. I could go to the home directory by doing cd$home. You see pwd now is home student. If I do cd ... I go up one level to just home. Another way to navigate is to use the pushd and popd commands. So I could do pushd temp, okay, and it's showing me my previous history. I was at temp and I was at home, and I go to temp. Now if I do popd, it puts me back at the home directory. Another thing I can do is cd-, And that takes me to the previous directory, just like popd did. So that's just some basic day-to-day practices of navigating directories that one does all the time on a Linux system.
There are two ways to identify paths. Absolute path name, which an absolute path name begins with the root directory and follows the tree, branch by branch, until it reaches the desired directory or file. Absolute paths always start with a slash. Or the relative path name. A relative path name starts from the present working directory. Relative paths never start with a slash. Multiple slashes between directories and files are allowed, but all but one slash between elements in the path name is ignored by the system. So if you have a bunch of slashes, it's valid, but it's just seen as just having a single slash by the system. Most of the time, it's most convenient to use relative paths, which require less typing. Usually you take advantage of the shortcuts provided by, use dot for present directory, dot for parent directory, or the tilde for your home directory. For example, suppose you're currently working in your home directory and wish to move to the /user/bin directory. The following two ways will bring you to the same directory from your home directory. There is the absolute path name method and the relative path name method. In this case, the absolute path name method requires less typing. Traversing up and down the file system tree can get tedious. The tree command is a good way to get a bird's eye view of the file system tree. Use tree-d just to view just the directories and to suppress listing the names. The following commands can help in exploring the file system.
Let's get started with how to explore the file system. To access /usr/local/lib from the /usr directory using absolute path, at command prompt type cd/usr/local/lib and press enter. Go back to /usr directory by typing cd/usr and press enter. To access /usr/local/lib from the /usr directory using relative path, at command prompt type cd local/lib and press enter. Get to the root directory at the command prompt, type the cd/command and press enter. To get a list of the files and directory in the present working directory, at the command prompt type the ls command and press enter. To get a list of hidden files and hidden directories, at the command prompt type the ls-a command and press enter. To get a tree view of the file system, at the command prompt type the tree command and press enter. To get a tree view of only directories in the file system, at the command prompt type the tree-d/command and press enter.
The in utility is used to create hard links and with the -s option. Soft links, also known as symbolic links or symlinks. These two kinds of links are very useful in Unix-based operating systems. Suppose that file 1 already exists. A hard link called file 2 is created with this command. Note that two files now appear to exist. However, a closer inspection of the file listing shows that this is not quite true. So we'll do ls-li file 1 name file 2, and the -i option to ls prints out in the first column the inode number, which is a unique quantity for each file object. This field is the same for both these files, so what is really going on here is that there's only one file, but it has more than one name associated with it, as indicated by the 2 that appears in the ls output. Thus, there was already another object linked to file 1 before the command was executed. Hard links are very useful and they save space, but you have to be careful with their use, sometimes in subtle ways. For one thing, if you remove either file 1 or file 2 in the example, the inode object and the remaining file name will remain, which might be undesirable, as it may lead to subtle errors later if you recreate a file of that name. If you edit one of the files, exactly what happens depends on your editor. Most editors, including V and gedit, will retain the link by default, but it's possible that modifying one of the names may break the link and result in the creation of two objects. Soft or symbolic links are created with the "-s option, as in ln-s file1 file3 or ls-li file1 file3. Notice file 3 no longer appears to be a regular file, and it clearly points to file 1 and has a different inode number. Symbolic links take no extra space on the file system, unless their names are very long. They're extremely convenient as they can easily be modified to point to different places. An easy way to create a shortcut from your home directory to long path names is to create a symbolic link. Unlike hard links, soft links can point to objects even on different file systems, partitions, and/or disks and other media, which may or may not be currently available or even exist. In the case where the link does not point to a currently available or existing object, you obtain a dangling link. The cd command remembers where you were last and lets you get back there with cd-. For remembering more than just the last directory visited, use push D to change the directory instead of cd. This pushes your starting directory onto a list. Using pop-D will then send you back to those directories, walking in reverse order. The most recent directory will be the first one retrieved with pop-D. The list of directories is displayed with the dirs command. Linux provides many commands that help you with viewing the contents of a file, creating a new file or an empty file, changing the timestamp of a file, and moving, removing, and renaming a file or directory. These commands help you in managing your data and files, and ensuring that the correct data is available at the correct location. In this section, you will learn how to manage files.
Let's get a feel for how to look at some of the lines in a given text file on your machine. So we have on all our Linux Foundation virtual machines a file called ready4.sh, which I'm using word count to show me it has 5,127 lines. If I just want to type the whole file out, I could do that with the cat utility. So let me just do that. But it went very, very fast. And in fact, if I do cat-n, it shows me the line numbers as it goes, and it is indeed 5127. The way to page your way through is to use the less utility. So then I would do less ready4.sh, and then I get one screen at a time. If I hit the space bar, I see the second screen, third screen, etc., and I can keep going all the way through the file as fast as I want. And by the way, I can also do the less-N option, and then I also get line numbers I did with cat-n. So similar thing. Now suppose I just want to look at the first few lines of the file. I could do head ready4.sh. And you see that only gave me, I believe, 10 lines. If I wanted to get 20 lines, I could just give that as an argument. Okay, so there we see the first 20 lines. Likewise with tail, by default I get the last 10 lines. If I wanted to see the last 20 lines, I would do tail-20. Yet if you want to have some fun, you can use the tac utility, where you'll notice that TAC is cat backwards, and that just gives you the entire file backwards. So these are day-to-day utilities one uses just to look at the contents of text files.
Touch is often used to set or update the access, change, and modify times of files. By default, it resets a file's timestamp to match the current time. However, you can also create an empty file using Touch. like this, touch and then the file name. This is normally done to create an empty file as a placeholder for a later purpose. Touch provides several useful options. For example, the -t option allows you to set the date and timestamp of the file to a specific value, as in touch -t and then we put the value and then the file name. Makedir is used to create a directory, such as makedir sampdir. It creates a sample directory named sampdir under the current directory. Makedir /user/sampdir will create a sample directory called sampdir under /user. Removing a directory is done with rmdir, or remove directory. The directory must be empty or the command will fail. To remove a directory and all of its contents, you have to do rm-rf. Note that mv does double duty in that it can simply rename a file or move a file to another location while possibly changing its name at the same time. If you're not certain about removing files that match a pattern you supply, it's always good to run rm interactively, rm-i, to prompt before every removal. rmdir works only on empty directories, otherwise you get an error. So while typing rm-rf is a fast and easy way to remove a whole file system tree recursively, it's extremely dangerous and should be used with the utmost care, especially when used by root. Recall that recursive means drilling down through all subdirectories, all the way down a tree. The ps1 variable is the character string that is displayed as the prompt on the command line. Most distributions set ps1 to a known default value, which is suitable in most cases. However, users may want custom information shown on the command line. For example, some system administrators require the user and the host system name to show up on the command line, as in this example. This could prove useful if you're working in multiple roles and want to be always reminded of who you are and what machine you are on. The prompt above could be implemented by setting the ps1 variable to the following. For example, you could do that with this command here. By convention, most systems are set up so that the root user has a # as their prompt.
Let's gain some experience with day-to-day basic file operations on a CentOS 8 stream system. This would be the same on any Linux system. So first let's create a couple of files. They could be empty or they could be small. One way to do it is to use the echo command and just say echo and direct actually nothing into file 1. Another way to do it is with the touch command. I'll just say touch file 2. Then if I do ls-a file 1 and file 2, I see two very small files, both created at the same time basically. If I want to rename one of them, I could rename it with the move command, like move file 1 to file 1 new name. And then if I do ls-l star file star, I see there it is. It has the new name now. If I want to remove them, I can simply say rm file 2, and it just worked. It's a good idea, though, to always use the I option for interactive when doing removal. Then I would say rm-i file 1 new name, and it'll ask me if I really want to do it. Many distributions will set up the I option to be the default, so that you always have a chance to change your mind about removing something before you do it. Now, how would I make a directory? I could do make dir, dir1. And in fact, I can make more than one directory on the same line. I can do make dir, dir2, and dir3. And if I look now, I see I have 3 different directories. They're all actually empty. So let me put a couple of files in one of the directories. So I'll do touch dir2 file 1, and I'll do touch dir2 file 2. So if I do ls-lr, just to see everything that's there in the directory files, so what I'll see, dir1 is empty, dir2 has these two files, and dir3 is also empty. Now the command for removing directories is rmdir. So let's say I just try to remove them all with rmdir dir star. You notice it got rid of dir1 and dir2, but it couldn't remove dir1 and dir3, I should say. It couldn't get rid of dir2 because there's files in it. To do that, instead of using rmdir, I would say rmrf dir2, and then that goes and descends into the directory and gets rid of all the files. Be very careful with the rm-rf command, because if you give the bad argument, you could even wipe out your whole system. But that is the standard way to get rid of a whole directory tree. So that's just some of the very basic commands for renaming files, moving them, creating directories, removing them, etc.
When commands are executed, by default, there are three standard file streams, or descriptors, always open for use: standard input, standard output, and standard error. Usually, standard input is your keyboard, and standard output and standard error are printed on your terminal. Standard error is often redirected to an error logging file, while standard in is supplied by directing input to come from a file or from the output of a previous command through a pipe. Standard out is also often redirected into a file. Since standard error is where error messages are written, usually nothing will go there. In Linux, all open files are represented internally by what are called file descriptors. Simply put, these are represented by numbers starting at 0. Standard in is file descriptor 0, standard out is file descriptor 1, standard error is file descriptor 2. Typically, if other files are opened in addition to these three, which are opened by default, they will start at the file descriptor 3 and increase from there. In the next section and in the chapters ahead, you'll see examples which alter where a running command gets its input, where it writes its output, or where it prints diagnostic or error messages. Through the command shell, we can redirect the three standard file streams so that we can get input from either a file or another command, instead of from our keyboard, and we can write output and errors to files or use them to provide input for subsequent commands. For example, if we have a program called do something that reads from standard in and writes to standard out and standard error, we can change its input source by using the less than sign, followed by the name of the file to be consumed for input data. Here's an example. If you want to send the output to a file, use the greater than sign, as in this example. Because standard error is not the same as standard out, error messages will still be seen on the terminal windows in the above example. If you want to redirect standard error to a separate file, you use standard error's file descriptor number 2, the greater than sign, followed by the name of the file you want to hold everything the running command writes to standard error. So here's how you would do that. A special shorthand notation can send anything written to file descriptor 2, standard error, to the same place as file descriptor 1, standard out. You can do it like this. Bash permits an easier syntax for the above, which is like so. The Unix/Linux philosophy is to have many simple and short programs or commands cooperate together to produce quite complex results, rather than have one complex program with many possible options and modes of operation. In order to accomplish this, extensive use of pipes is made. You can pipe the output of one command or program into another as its input. In order to do this, we use the vertical bar pipe symbol between commands, as in this example here. This represents what we often call a pipeline and allows Linux to combine the actions of several commands into one. This is extraordinarily efficient because Command 2 and Command 3 do not have to wait for the previous pipeline commands to complete before they can begin hacking at the data in their input streams. On multiple CPU or core systems, the available computing power is much better utilized and things get done quicker. Furthermore, there is no need to save output in temporary files between the stages in the pipeline, which saves disk space and reduces reading and writing from disk, which is often the slowest bottleneck in getting something done. Being able to quickly find the files you are looking for will save you time and enhance productivity. You can search for files in both your home directory space or in any other directory or system or location on the system. The main tools for doing this are the locate and find utilities. We'll also show how to use wildcards in Bash in order to specify any file which matches a given generalized request. The locate utility program performs a search taking advantage of a previously constructed database of files and directories on your system, matching all entries that contain a specified character string. This can sometimes result in a very long list. To get a shorter and possibly more relevant list, we can use the grep program as a filter. Grep will print only the lines that contain one or more specified string, as in this example, which will list all the files and directories with both zip and bin in their name. We'll cover grep in much more detail later. Notice the use of the pipe or the vertical line to pipe the two commands together. Locate utilizes a database created by a related utility, update-db. Most Linux systems run this automatically once a day. However, you can update it at any time by just running update-db from the command line as the root user.
Let's get some practice with locating and finding files on an Ubuntu system. So suppose I want to find all files that have the string LFS 300 in them. So I could do locate LFS 300. And it finds indeed just one file that's in the home student directory, on a subdirectory there. And I could also find it by doing find dot, meaning the current directory name, LFS 300 star, and then I'll see it finds it. And if I want to find out a little more, I can give the ls option, which will show me who owns it, what group they're in, the length of the file, the inode, the date, etc. Now, if I create another file just by doing echo into LFS 300, so it creates essentially an empty file, the find command will find the new file as well as the old one, but the locate command will not, because I need to update the database that the locate command uses. And I do that by running as root, so I need sudo update db. And that was pretty quick. And then if I say locate it, now it finds both files. Okay, and just to get rid of the file I didn't really need, I'll remove it. I'll run update db again. Well, I need it to be root, so I have to say sudo. And then once again, locate fs300 won't find this new file. Now I can configure update db and locate to do a bunch of things. So if I go to the etc directory, you'll see there's a file called updatedb.conf, and it controls where updatedb does not look, where locate does not look. So for instance, under prune tasks, it says don't look in these places like the temp directory because they're temporary and you don't want to keep track of what's there particularly. And prunefs, these are file systems, really pseudo file systems that are not real file systems that you shouldn't look in, because they're also the contents change every time you boot, let's say. So for instance, you don't look in the proc directory or the sysfs directory or the dev directory, devfs directory, because these things disappear every time you reboot. And so it's pretty easy to configure. There's some other things you can do, which you can learn by looking at the documentation on your system.
You can search for a file name containing specific characters using wildcards. To search for files using the question mark wildcard, replace each unknown character with question mark. For example, if you know only the first two letters are BA of a three-letter file name without an extension, you can type this. To search for files using the wildcard, replace the unknown string with the asterisk. For example, if you remember only that the extension was .out, type ls asterisk .out.
Let's get some experience using wildcards on an Ubuntu system. So I've gone to the var log directory, and let me just do an ls to see what's there. So for instance, let me use the du or disk usage utility, which tells me all the bytes that are being used by a given file or subdirectory. I could do something like du.sh a star, and you'll see these are all the different things under A. Some are directories like app, the others are just files. If I only wanted to look at ones which have log in the name, I could do du.sh a star log star. And so only ones that have log in their names. If I only wanted to look at the ones that start from the letter P or later in the alphabet, I could do du.sh a, and then I could say square brackets P through Z star. You see, and it neglected the alternative ones, which would have done that. If I just want to look at ones which have a certain character in them, I could do something like du star dot one character dot star. So those are all the ones that have a substring in them with one character. Here it's always a number, but it wouldn't have to be, surrounded by periods on both sides. Now you have to be careful with wildcards that the system doesn't, quote, glob what you are doing, the string that you're putting in. So to give you an example, you'll notice there's a bunch of different files here that start with the name VMware. Well, they're all over in the right column here. So suppose I try to do apt-get install VMware star, and I should make that sudo. Well, it's actually looking for packages with all these names, like VMware Network 1, VM VSC Root 2, that log, and there are, of course, no packages with silly names like that, but I could do something like this now. Let me put the VMware star in quotes. And you see it actually did find things. It found two packages, VMware NSX Common, VMware Manager, and it wants to install them, and it needs these other utilities in order for them to work. I'm not going to do this because I don't need these guys, so I'll just say no. So when you put something in quotes, it says don't look in the current directory to like fill out the names to expand what you're doing. Instead, look in this case in the database of packages. So you have to be careful, and you'll often see people use quotes even when there's no need for them, just to be safe. So that's a little bit of demonstration of the use of wildcards.
Find is an extremely useful and often used utility program in the daily life of a Linux system administrator. It recurses down the file system tree from any particular directory or set of directories and locates files that match specified conditions. The default path name is always the present working directory. For example, administrators sometimes scan for potentially large core files, which contain diagnostic information after a program fails. They're more than several weeks old in order to remove them. It's also common to remove files that are not essential or that are outdated in the /tmp directory, especially those that have not been accessed recently. Many Linux distributions use shell scripts that run periodically through cron to perform such house cleaning. When no arguments are given, find lists all files in the current directory and all of its subdirectories. Commonly used options to shorten the list include -name, which only lists files with a certain pattern in their name, -iname, also ignore the case of the file names, and -type, which will restrict the results to files of a certain specified type, such as D for directory, L for symbolic link, or F for a regular file. Here's how you can search for files and directories named GCC. Here's how to search only for directories named GCC. Here's how to search for or only for regular files named GCC. Another good use of find is being able to run commands on the files that match your search criteria. The -exec option is used for this purpose. To find and remove all files that end with .swp, you can use this. The squiggly brackets are a placeholder that will be filled with all the file names that result from the find expression, and the preceding command will be run on each one individually. Please note that you have to end the command with either a semicolon, including the single quote, or a /semicolon. Both forms are fine. One can also use the -OK option, which behaves the same as -exec, except that find will prompt you for permission before executing the command. This makes it a good way to test your results before blindly executing any potentially dangerous commands. It is sometimes the case that you wish to find files according to attributes, such as when they were created, last used, or based on their size. It's easy to perform such searches. To find files based on time, you can use this. Here, -c time is when the inode metadata, or the file ownership, the permissions, last changed. It's often, but not necessarily, when the file was first created. You can also search files based on when they were accessed or last read, or based on when they were modified or last written. The number is the number of days and can be expressed in either a number n, that means exactly that value, plus n, which means greater than the number, or minus n, which means less than that number. There are similar options for times in minutes, as in the -cmin, -amin, and -mmin. To find files based on sizes, you can do this. Note that the size here is in 512 byte blocks by default. You can also specify bytes, kilobytes, megabytes, gigabytes, etc. As with the time numbers above, file sizes can also be exact numbers. For details, consult the man page for find. For example, to find files greater than 10 megabytes in size and running a command on those files, you can use this command.
Let's gain some experience using a very powerful find utility on an Ubuntu system, and I'll work in the var log directory. So suppose I wanted to see every file here that's underneath var log, and let me do it as sudo because otherwise it will give me error messages about not having permissions to look at some files. So I'll do sudo find dot, and I get a very long list of every single file and directory that's underneath here. If I wanted to restrict it just to directories, I would do type D. And you'll see this just shows me the directories and subdirectories, okay? Because like some of them, like live-virt, have multiple directories. If I add to that another parameter, max depth 1, you see, it suppressed the subdirectories. Here I only see live-virt now, so I only went down a depth of 1, and actually I could do 2, 3, or whatever is necessary, though here it doesn't go that deep anyway. Now you can always add commands to any find command, so I could do find dot type F, and then I can say exec grep -h log, and I put in that parentheses pair there, and then let's say slash semicolon. You can also do single dash semicolon single dash, and it searched through every single file that had the word log in it and printed out all the different things that were there. Or to keep it a little simpler, I could have done exec just ls-l, and it would give me listings of all these files. Okay. Now there actually is a ls option built into find, so I didn't really have to do that, and it will just show me that kind of information. There's other things I can do, like find size 0. It's finding all the files. I should have done sudo, but all the files that have a size of 0. And if I want to verify that, I'll add the ls option. You see these are all files of the name with size 0. You can also do things like find, let's say I want to find everything that's newer than this file, btemp here. I could do something like sudo find dot newer btemp, and it showed me everything that's been done since then. There's a million options to find. It can be used in a lot of complicated ways. You can negate any parameter you want to put in by saying not. You can combine different search criteria, and I recommend heavily that you really read up on find if you're going to use it, because it's a little hard to describe in a few seconds, but there's a million things you can do with it.
The core parts of a Linux distribution and most of its add-on software are installed via the package management system. Each package contains the files and other instructions needed to make one software component work well and cooperate with the other components that comprise the entire system. Packages can depend on each other. For example, a package for a web-based application written in PHP can depend on the PHP package. There are two broad families of package managers, those based on Debian and those which use RPM as their low-level package manager. The two systems are incompatible, but broadly speaking, provide the same features and satisfy the same needs. There are some other systems used by more specialized Linux distributions. In this section, you will learn how to install, remove, or search for packages from the command line using these two package management systems. Both package management systems operate on two distinct levels. A low-level tool, such as dpkg or RPM, takes care of the details of unpacking individual packages, running scripts, getting the software installed correctly, while a high-level tool such as apt-get, DNF, yum, or zypper works with groups of packages, downloads packages from the vendor, and figures out dependencies. Most of the time, users need to work only with the high-level tool, which will take care of calling the low-level tool as needed. Dependency resolution is a particularly important feature of the high-level tool, as it handles the details of finding and installing each dependency for you. Be careful, however, as installing a single package could result in many dozens or even hundreds of dependent packages being installed. The Advanced Packaging Tool, apt, is the underlying package management system that manages software on Debian-based systems. While it forms the backend for graphical package managers, such as the Ubuntu Software Center and Synaptic, its native user interface is at the command line, with programs that include apt or apt-get and apt-cache. DNF is the open source command line package management utility for the RPM compatible Linux systems that belongs to the Red Hat family. DNF has both command line and graphical user interfaces. Fedora and RHEL 8 replaced the older yum utility with DNF, thereby eliminating a lot of historical baggage, as well as introducing many nice new capabilities. DNF is pretty much backwards compatible with yum for day-to-day commands. Zypper is the package management system for the SUSE or OpenSUSE family, and it's also based on RPM. Zypper also allows you to manage repositories from the command line. Zypper is fairly straightforward to use and resembles DNF or yum quite closely. To learn the basic package commands, take a look at these basic packaging commands.
Let's get some practice with the basic low-level command for the Debian packaging system, dpkg, or dpackage. So to get a list of all the packages on the system, I can simply type dpkg --list. And I'll just pipe that into list because it's a long list. Okay? Actually, if I don't use list for some reason, it's more compact. Okay, so there are a lot of different packages on the system. Now, if I want to see some information just about a particular package, I could just grep, let's say, bzip2 to see what's going on with bzip2. And that's the information about bzip2. That tells us the version number, the architecture, which here is AMD64, and its description as a high-quality block sorting file compressor utility. So it's a more advanced program with better compression than gzip or the old-fashioned zip program. If I want to see what's actually contained in that package, I can do dpkg list files and then the name of it, and then I'll go slower by putting it into less. And you'll see there's the executables in the bin directory. And then what's under user is basically documentation. Under user share doc, user share man, etc. If I try to remove the package, let's see what happens. So do sudo dpkg. I, of course, have to have root privilege to remove the package. So I'm removing bzip2, dpackage remove bzip2. And it's telling me I cannot do this because I need the developer in package, dpkg-dev. That would be headers and stuff for programs which use this in a library version. And file roller, which is an archive extractor that's common on Linux systems. So I would have to remove all three of them. We'll see later when we use tools like apt-get, it's easier to deal with these dependencies. We'll now get some practice using the low-level RPM command in order to look at a package, try to remove it, etc. So we're going to type rpm-qa for query and look at all packages on the system. And then we're going to grep to look for the package bzip2. Okay, and you see there's actually two RPM packages which have bzip2 in their names. The actual bzip2 program and then bzip2 libs, which is libraries that depend on bzip2. So let's take a look more at information about bzip2. If I do rpm-q for query, I for information, and then L for a list of files, and that's a lot, so I'll pipe it through less. Oops, I forgot to give the name of the package, so bzip2. You see the name is bzip2. You see it's version 1.06. We see its source RPM here. We see when it was released in November 2015 out of centos.org. And then a description of what it does. It's a freely available, patent-free, high-quality data compressor, etc. And then a list of the files that are part of bzip2. If I want to get a little bit more detailed look at what's in there, I could do something a little fancier like rpm.ql bzip2 would just list the files. And then I'll make that a shell command and substitute for it and do an ls-lf on that. So this will give me a detailed listing, and then I'll pipe it into less. And these are the actual files that are in the package in a little bit more detail, like their length and what type of files. You'll notice, for instance, bunzip2 and bzip2 are really the same file. It's just a symbolic link, and the system knows what to do, or I should say the application knows what to do, whether to zip or unzip depending on how it's called. Now let's see what happens if I try to remove the package. So should be root to do that, so do an sudo, and then I'll do rpm-e for erase, and then just to be extra careful, I'll use the --test, which means it won't actually do anything with this option. It'll just see if it could do it. bzip2, so I try to remove it. And it's telling me that I can't do that because it's needed by those following 3 packages, as well as the file roller program, which is an archiving program present on basically all Linux distributions. And then I can get a little more information in a different way with rpm-q --what provides bzip2. And you'll see it's the bzip2 package. And if I do what requires, I get the same information about the 3 packages that need to have bzip2 installed for them to behave properly and not crash or anything. A little bit later, we're going to discuss yum and zypper, and also DNF, which are higher level programs that can handle dependencies in a robust fashion. RPM is really designed for individual packages which are listed on the command line, or groups of packages listed on the command line. Let's get some practice using DNF from the command line on a recent Fedora system. So in order to do that, first I'll have to bring up the command line. So I'll do that with activities, and I'll click on the terminal icon at the bottom, and I've got a nice command line terminal, and I'll make it a little bit bigger because the font's bigger, that is, because it's hard to see with the smaller fonts. And then first let's get a list of all packages that have the string bzip2 in their name. So I'll do that with DNF list. And the first packages that will come up will be the ones that are already installed. So let me scroll up a little because there's a really long list here. So there I have the actual program bz2, a development package in case I want to write code that uses bzip2 internally. And then bzip2 libs would be used by programs that have bzip2 already built into them. The 2 I'm going to be interested in installing here are the lbzip2 packages. lbzip2 is a parallel version of bzip2 that can separate the amount of work into a number of pieces that can be done simultaneously. So, for instance, if you had 4 processors or cores, you could split the work up into 4 pieces and do them all at the same time and then merge them at the end. And in theory, it could run almost 4 times as quickly. So let's try to install the utilities package. I'll do sudo dnf install lib bzip2. Yeah, I guess it's lbzip2 bzip2 utils. And you'll see, yes, it's happy to do that, but it also needs the lbzip2 package, which it depends on. So I'll say yes. I'll just type Y. And it will install the 2 packages. I probably have a program now called lbzip2, but let's check if that's the case. With which. And yes, I do. So I could go ahead and use it now if I wanted. If I don't really want these installed and I want to clean up with them, I could do something like sudo dnf remove lbzip2. And you notice it's happy to remove it, but it's telling me that because lbzip2 utils depends on lbzip2, if I remove lbzip2, I better remove them both. Otherwise, I'll have an unsatisfied dependency, so I'll just say yes. So that's just a really simple example of using DNF from the command line. Unfortunately, recent Red Hat-based systems do not have a really good graphical package management utility. Fedora has something called DNF Dragon, but it can be rather slow to load and a little bit buggy. And there's nothing at all for Red Hat 8 or CentOS 8. So experienced developers will just always tend to do things from the command line. Let's demonstrate some basic package management functions on an OpenSUSE system using the zipper utility. So first, let's look for all packages with zipper search that have the string new plot in them. And we see a number of packages. Let's concentrate on the documentation package. So suppose I try to install that, and for that I have to be a super user for an installation. So I do sudo zipper install new plot doc. And you notice it's telling me I not only have to install newplot.doc, I would have to install newplot, which is the actual program that newplot.doc -doc documents. So I'll say sure, yes. And it's been done successfully. If I want to get some information about the package, I can do rpm-qi newplot-doc, and for this, once again, I do not have to be root. And it's telling me the name, the version, the size, all sorts of things, and under the purpose, it's telling me it includes the man and the info pages for this rather useful plotting program. Now suppose I want to remove this package. I can do zipper remove GNU plot. Let's say I try to remove GNU plot, not newplot.doc. And it's telling me that if I remove new plot, I also have to remove newplot.doc -doc, because otherwise there would be unmet dependencies. So I'll say yes for sure. And now both of them are gone. So that's basic steps you would take to look for a package, install it, get some information about it, and remove it using zipper. So let's do some basic package management on an Ubuntu system using Debian packaging. We're going to use the high-level utilities which understand dependencies, apt-cache and apt-get. So first, let's look for all packages that contain the string wget2. So we do that with apt-cache search wget2. And it comes up with wget2 and wget2 dev. This is an enhancement to the standard wget utility, which is used for recursive downloading of the content of a website or some other kinds of resources. So let's just try and install. So I do sudo apt-get install wget2-dev. And it's telling me it also needs to install live wget0 and wget2. It shouldn't be that surprising that you need to install the base packages on which the development package is built on. And it will download 264 kilobytes of archives, but once everything's installed, it will expand out to 805 kilobytes. So let's just say yes. I'll type Y. And it quickly goes ahead and does all that. Now suppose I want to remove wget2-dev. Well, more interesting, let's try to remove wget itself. So what is it doing? Oh, I shouldn't have removed wget, I meant wget2. Wget I do not want to remove, so I'll type it again with the 2. And you see it wants to remove wget2-dev as well, because without wget2-dev doesn't have much meaning. Okay, and we no longer need the live wget0. It's sort of orphaned out, but we'll leave it there for now. So I'll just say yes. And I have removed things from my system. So that's the most basic operations you would need to do on an Ubuntu system using Debian packaging.
You have completed Chapter 7. Let's summarize the key concepts we covered. Virtual terminals, or VT, in Linux are consoles or command line terminals that use the connected monitor and keyboard. Different Linux distributions start and stop the graphical desktop in different ways. A terminal emulator program on the graphical desktop works by emulating a terminal within a window on the desktop. The Linux system allows you to either log in via text terminal or remotely via the console. When typing your password, nothing is printed to the terminal, not even a generic symbol to indicate that you typed. The preferred method to shut down or reboot the system is to use the shutdown command. There are two types of path names, absolute and relative. An absolute path name begins with the root directory and follows the tree branch by branch until it reaches the desired directory or file. A relative path name starts with the present working directory. Using hard and soft symbolic links is extremely useful in Linux. CD remembers where you were last and lets you get back there with CD-. Locate performs a database search to find all file names that match a given pattern. Find locates files recursively from a given directory or set of directories. Find is able to run commands on the files that it lists when used with the -exec options. Touch is used to set the access, change, and edit times of files, as well as to create empty files. The Advanced Packaging Tool, apt, this package management system is used to manage installed software on Debian-based systems. You can use the DNF command line package development utility for the RPM-based Red Hat family Linux distributions. The Zipper package management system is based on RPM and used for OpenSUSE. By the end of this chapter, you should be able to use different sources of documentation, use the man pages, access the new info system, use the help command and the --help option, use other documentation sources. Whether you are an inexperienced user or a veteran, you'll not always know or remember the proper use of various Linux programs and utilities. What is the command to type? What options does it take, etc. You'll need to consult help documentation regularly. Because Linux-based systems draw from a large variety of sources, there are numerous reservoirs of documentation and ways of getting help. Distributors consolidate this material and present it in a comprehensive and easy-to-use manner. Important Linux documentation sources include the man pages, short for manual pages, new info, the help command and --help option, other documentation sources like the Gentoo handbook. The man pages are the most often used source of Linux documentation. They provide in-depth documentation about many programs and utilities, as well as other topics, including configuration files and programming APIs for system calls, library routines, and the kernel. They are present on all Linux distributions and are always at your fingertips. The man pages infrastructure was first introduced in the early Unix versions in the beginning of the 1970s. The name man is just an abbreviation for manual. Typing man with a topic name as an argument retrieves the information stored in the topic's man pages. The man program searches, formats, and displays the information contained in the man page system. Because many topics have copious amounts of relevant information, output is piped through a pager program, such as less, to be viewed one page at a time. At the same time, the information is formatted for a good visual display. A given topic may have multiple man pages associated with it, and there is a default order determining which one is displayed when no options or section number is specified. To list all pages on the topic, use the -F option. To list all pages that discuss a specific topic, even if the specified topic is not present in the name, use the -K option.
let's use the man utility to get some information about sockets on our system. If I just type man socket, I get chapter 2 of the Linux Programmer's Manual. I get the page in there in chapter 2 that has to do with sockets. And this is a pretty general page that tells me a lot of information about sockets and different protocols that they can use. If I want to get a list of all the pages that are called socket, I do man-f socket. You see there's actually 5 of them in different chapters. That, by the way, is exactly the same as saying what is socket. So man-f and apropos are the same. If I want to see a particular page, say chapter 7, I can do man7 socket, and I'm getting the man page in chapter 7, which is rather detailed. If I want to see them all at once, I can say man-a socket for all, I guess. And I can space my way through this one. If I hit Q, it's telling me if I hit return, I'll see the next one 3P, so let's do that. I'll hit Q again. You see, if I want to get out rather than going through the rest of them, the next one would be 7, I can hit Control C. Control D would just skip the next one. If I want to see all man pages that have the word socket in their basic description, I do that with man-K. And it's a rather long list because sockets are pretty basic and involve all sorts of things on your system. Man-K is exactly the same as typing apropos socket, and I get the exact same thing. So that's just some basic day-to-day functioning of using man to get information. You should play around with different man pages and look at the real contents in them and see how they differ from page to page.
The next source of Linux documentation is the GNU Info System. This is the GNU project standard documentation format, which it prefers as an alternative to man. The info system is basically freeform and supports linked subsections. Functionally, info resembles man in many ways. However, topics are connected using links, even though its design predates the World Wide Web. Information can be viewed through either a command line interface, a graphical help utility, printed, or viewed online. Typing info with no arguments in a terminal window displays an index of available topics. You can browse through the topic list using the regular movement keys, arrows, page up, and page down. You can view help for a particular topic by typing info topic name. The system then searches for the topic in all available info files. Some useful keys are Q to quit, H for help, and Enter to select a menu item. The topic which you view in an info page is called a node. This table lists the basic keystrokes for moving between nodes. Nodes are essentially sections and subsections in the documentation. You can move between nodes or view each node sequentially. Each node may contain menus and linked subtopics or items. Items function like browser links and are identified by an asterisk at the beginning of the item name. Named items, outside a menu, are identified with double colons at the end of the item name. Items can refer to other nodes within the file or to other files.
Let's gain some experience using the info command for documentation. So suppose I type info make, I will get information about the make utility used by all programmers. And this takes me to the top of the info page or the head node. If I want to look for a particular topic, I can hit slash, and you'll see at the bottom it's prompting me for a search, so I'll say example. And it brought me down here to rule example. If I just hit return, I get that page. Now at the top you'll notice it says the node is root example, the next one is rule syntax. So if I hit an N, I get the rule syntax. It says the next one is prerequisite types. If I hit N again, I get prerequisite types. If I hit P, I will go back to the previous one. So I hit P, rule syntax. If I want to look again, for example, I can just hit the slash again, and it's prompting me for the same string, so I'll just hit return. and I'm finding a later example about wildcard examples, and if I hit return, I find out above that. If I want to go all the way up, I can hit a U. It takes me to the top of section 4.4. I hit U again, I'm at chapter 4. I hit U again, I'm at the very top of everything. If I want to get information on the various keystroke bindings, I can hit an H for help. And you'll see in the bottom window, where the focus is shifted to, it lists all the possible keystrokes and what they can do. So that's basically how I would use info. If I hit Q, I am out of it. And the rest you can learn by navigating within the info page of any topic that interests you.
Another important source of Linux documentation is the use of the -- help option. Most commands have an available short description which can be viewed using the -- help or the -h option along with the command or application. For example, to learn more about the man command, you can type man -help. The -- help option is useful as a quick reference and it displays information faster than the man or info pages. When running within a bash command shell, some popular commands, such as echo and cd, actually run especially built-in bash versions of the commands rather than the usual binaries found on the file system. It's more efficient to do so as execution is faster because fewer resources are used. One should note that there can be some, usually small differences in the two versions of the command. To view a synopsis of these built-in commands, you can simply type help as shown in this screenshot. For these built-in commands, help performs the same basic function as the -h and -help arguments perform for standalone programs. In addition to the man pages, the new info system, and the help command, there are other sources of Linux documentation. Some examples of which include desktop help system, package documentation, and online resources. You have completed Chapter 8. Let's summarize the key concepts covered. The main sources of Linux documentation are the man pages, new info, and the help options and commands, and a rich variety of online documentation sources. The man utility searches, formats, and displays man pages. The man pages provide in-depth documentation about programs and other topics about the system, including configuration files, system calls, library routines, and the kernel. The new info system was created by the new project as its standard documentation. It's robust and it's accessible via command line, web, and graphical tools. Short descriptions for commands are usually displayed with the -h or -help argument. You can type help at the command line to display a synopsis of built-in commands. There are many other help resources both on your system and on the internet. By the end of this chapter, you should be able to describe what a process is and distinguish between types of processes, enumerate process attributes, manage processes using PS and top, understand the use of load averages and other process metrics, manipulate processes by putting them in background and restoring them to foreground, use at, cron, and sleep to schedule processes in the future or pause them. A process is simply an instance of one or more related tasks, threads, executing on your computer. It's not the same as a program or a command. A single command may actually start several processes simultaneously. Some processes are independent of each other, and others are related. A failure of one process may or may not affect the others running on the system. Processes use many system resources, such as memory, CPU cycles, and peripheral devices, such as network cards, hard drives, printers, and displays. The operating system, especially the kernel, is responsible for allocating a proper share of these resources to each process and ensuring overall optimized system utilization. A terminal window, one kind of command shell, is a process that runs as long as needed. It allows users to execute programs and access resources in an interactive environment. You can also run programs in the background, which means they become detached from the shell. Processes can be of different types according to the task being performed. Here are some different process types, along with their descriptions and examples. A critical kernel function called the scheduler consistently shifts processes on and off the CPU, sharing time according to the relative priority, how much time is needed, and how much has already been granted to a task. When a process is in a so-called running state, it means it's either currently executing instructions on a CPU or it's waiting to be granted a share of time, a time slice, so it can execute. All processes in this state reside on what is called a run queue, and on a computer with multiple CPUs or cores. There's a run queue on each CPU or core. However, sometimes processes go into what is called a sleep state, generally when they're waiting for something to happen before they can resume, perhaps for the user to type something. In this condition, a process is said to be sitting in a wait queue. There are some other less frequent process states, especially when a process is terminating. Sometimes a child process completes, but its parent process has not asked about its state. Amusingly, such a process is said to be in a zombie state. It's not really alive, but still shows up in the system's list of processes. At any given time, there are always multiple processes being executed. The operating system keeps track of them by assigning each a unique process ID, or PID number. The PID is used to track process state, CPU usage, memory use, precisely where resources are located in memory, and other characteristics. New PIDs are usually assigned in ascending order as processes are born. Thus, PID1 denotes the init process, and succeeding processes are gradually assigned higher numbers. The table explains the PID types and their descriptions. At some point, one of your applications may stop working properly. How do you eliminate it? To terminate a process, you can type kill-sigkill PID or kill-9 PID. Note, however, you can only kill your own processes. Those belonging to another user are off limits, unless you're root. Many users can access a system simultaneously, and each user can run multiple processes. The operating system identifies the user who starts the process by the real user ID, or the RUID, assigned to the user. The user who determines the access rights for the users is identified by the effective UID, the EUID. The EUID may or may not be the same as the RUID. Users can be categorized into various groups. Each group is identified by the real group ID, or the RGID. The access rights of the group are determined by the effective group ID, the EGID. Each user can be a member of one or more groups. Most of the time, we ignore these details and just talk about the user ID, the UID, and the group ID, GID. At any given time, many processes are running on the system. However, a CPU can actually accommodate only one task at a time, just like a car can have only one driver at a time. Some processes are more important than others, so Linux allows you to set and manipulate process priority. Higher priority processes get preferential access to the CPU. The priority for a process can be set by specifying a nice value or niceness for the process. The lower the nice value, the higher the priority. Low values are assigned to important processes, while high values are assigned to processes that can wait longer. A process with a high nice value simply allows other processes to be executed first. In Linux, a nice value of -20 represents the highest priority, and +19 represents the lowest. While this may sound backwards, this convention goes back to the earliest days of Unix. You can also assign a so-called real-time priority to time-sensitive tasks, such as controlling machines through a computer or collecting incoming data. This is just a very high priority and is not to be confused with what is called hard real-time, which is conceptually different and has more to do with making sure a job gets completed within a very well-defined time window.
So now let's show how to see what the niceness or priority of a process is and how you can change it with the renice command, or how you can do it actually from a graphical user interface. So let's look at the processes in this current screen with the ps command, which we will discuss in detail later, and we see that this current bash shell is 3077. To see the priority, I can run ps with the options lf, and there you see 3077 here is the bash command, and the niceness is 0. So let's try to change the niceness. I can do renice plus 5, 3077. And you see it did change the priority to 5, which I can see once again with the ps command. It has made it 5 here. Notice that the child process I ran off there, the command pslf, also has a niceness of 5. So anything else I create in this shell will have that new niceness. So this is a lower priority. Remember, increasing the niceness lowers the priority. So now suppose I try to increase the priority by decreasing the niceness to -5. You notice it says I can't do that. That's because only the super user or root is allowed to increase the priority of a process. But if I type the same command over again with sudo, it worked just fine, and I can verify that once again with pslf. And there you see it's set up to be -5 now, as well as the new ps command that I issued. Now, if I want to do this from a graphical utility, I can run GNOME System Monitor. I'll start from the command line here, though I could get it from a menu. And this is on the first possible screen here on processes. So if I hear that was process 3077, it's right here. And you notice it says priority high. I could right click on there and I can go to change priority, and then I can just say low, and now you see that it's low. And if I get out of the graphical utility and I look at the niceness again, you see now the priority has come up to 5. Not the niceness of 5, so that means it's low priority again. So that's how you can manipulate the priority of a process from the command line or from a graphical utility.
The load average is the average of the load number for a given period of time. It takes into account processes that are actively running on a CPU, considered runnable but waiting for a CPU to become available, or sleeping, i.e. waiting for some kind of resource to become available. The load average can be viewed by running w, top, or uptime. The load average is displayed using 3 numbers, such as 0.45, 0.17, and 0.12 in this screenshot. Assuming our system is a single CPU system, the 3 load average numbers are interpreted as follows. 0.45 means for the last minute the system has been 45% utilized on average. 0.17 means for the last 5 minutes utilization has been 17%. And 0.12 is for the last 15 minutes utilization has been 12%. If we saw a value of 1 in the second position, that would imply the single CPU system was 100% utilized on average over the past 5 minutes. This is good if we want to fully use a system. A value over 1 for a single CPU system implies that the system was overutilized. There were more processes needing CPU than CPU was available. If we had more than one CPU, say a quad CPU system, we would divide the load average numbers by the number of CPUs. In this case, for example, seeing a 1-minute load average of 4.0 implies that the system as a whole was 100%, 4 divided by 4, utilized during the last minute. Short-term increases are usually not a problem. A high peak you see is likely a burst of activity, not a new level. For example, at startup, many processes start and then activity settles down. If a high peak is seen in the 5 and 15-minute load averages, it may be cause for concern. Linux supports background and foreground job processing. A job in this context is just a command launched from a terminal window. Foreground jobs run directly from the shell, and when one foreground job is running, other jobs need to wait for shell access, at least in that terminal window if using the GUI, until it's completed. This is fine when jobs complete quickly, but this can have an adverse effect if the current job is going to take a long time, even several hours, to complete. In such cases, you can run the job in the background and free the shell for other tasks. The background job will be executed at lower priority, which in turn will allow smooth execution of the interactive tasks. And you can type other commands in the terminal window while the background job is running. By default, all jobs are executed in the foreground. You can put a job in the background by suffixing and or the ampersand to the command. For example, updatedb ampersand. You can either use Ctrl-Z to suspend a foreground job or Ctrl-C to terminate a foreground job, and you can always use the BG and FG commands to run a process in the background and foreground respectively. The Jobs utility displays all jobs running in the background. The display shows the job ID, state, and command name as shown here. Jobs-L provides the same information as jobs and adds the PID of the background jobs. The background jobs are connected to the terminal window, so if you log off, the jobs utility will not show the one started from that window. PS provides information about currently running processes keyed by PID. If you want a repetitive update of this status, you can use top or other commonly installed variants such as htop or atop from the command line, or invoke your distribution's graphical system monitor application. PS has many options for specifying exactly which tasks to examine, what information to display about them, and precisely what output format should be used. Without options, PS will display all processes running under the current shell. You can use the -U option to display information of processes for a specified username. The command PS-EF displays all the processes in the system in full detail. The command PS-ELF goes one step further and displays one line of information for every thread. Remember, a process can contain multiple threads. PS has another style of option specification, which stems from the BSD variety of Unix, where options are specified without preceding dashes. For example, the command PS-AUX displays all processes of all users. The command PS-AXO allows you to specify which attributes you want to view. This screenshot shows a sample output of PS with the AUX and AXO qualifiers.
The PS utility is used very often at the command line to gather information about what is running on the system, about the various processes and tasks which are running, what resource they were using, what relationship they have to each other, etc. If I just type PS without any arguments, I get the processes which have been launched underneath this particular terminal window. And in order to make it more interesting, I have a background processes running. I have a cat, a Nautilus, which is the file manager, and evince, which is the PDF viewer. I can get more information if I type PS-F, which you see now also tells me the parent process ID. So you notice bash has a process ID of 2942, and that's the parent process for both the cat and the Nautilus, which I launched directly out of the shell, as well as the PS command itself. The evince command has something else as a parent for complicated reasons having to do with how the GNOME shell runs. If I want to get a different piece of information, I can do PS-L. And now I am also seeing information in these two columns about the priority and the niceness, which on most Linux systems is just a numerical shift, okay, from a neutral niceness of 0 means the default priority of 80, which is what all normal processes start out with. Okay. Now, I can do more than this if I want to give additional arguments. So I do ps-elf, this will tell me about all processes on the system, and let me type it into less so it doesn't go too quickly. So you can see this is everything which is actually running on my system. You'll notice that the first bunch of processes in this rather long list all have these square brackets around them. That means they were not started by a user program. They're running inside the kernel to do various kinds of background tasks that run in the kernel all the time, handle moving things from one CPU to another, for instance, and all kinds of other things. And you'll see they have different priorities. They minus 20 here, minus 20 there. That means they're higher priorities. Okay, it's kind of backwards. The lower the priority number here, the higher the priority is. If I page down to the bottom, I will eventually get to tasks which are not running inside the kernel, which are running, for instance, under my name here, Coop. As you see, these are the actual user processes, and they're quite a bit different. Now, one reason the ps command can be a little confusing is that there are different kinds of options, those which have a dash and those which do not. So, for instance, ps-e is different than ps space e. One commonly set of options is ps-aux without a dash. And there you see one nice additional piece of information is the percentage of CPU being used. And of course, there isn't much going on in the system right now, so that tends to be 0. So you can customize what the output of the ps command is. If you look at the man page for ps, you'll see there's ways to have it print out only the columns that you want if you want to produce some customized reports, etc. But a standard Linux system administrator probably uses ps every day for one thing or another.
PS tree displays the processes running on the system in the form of a tree diagram, showing the relationship between a process and its parent process, and any other processes that it created. Repeated entries of a process are not displayed, and threads are displayed in curly braces. While a static view of what the system is doing is useful, monitoring the system performance live over time is also valuable. One option would be to run ps at regular intervals, say every few seconds. A better alternative is to use top to get constant real-time updates, until you exit by typing q.top. This clearly highlights which processes are consuming the most CPU cycles and memory, using appropriate commands from within top. The first line of the top output displays a quick summary of what is happening in the system, including how long the system has been up, how many users are logged on, and what is the load average. The load average determines how busy the system is. Load average of 1.00 per CPU indicates a fully subscribed but not overloaded system. If the load average goes above the value, it indicates that the processes are competing for CPU time. If the load average is very high, it might indicate that the system is having a problem, such as a runaway process, a process in a non-responding state. The second line of the top output displays the total number of processes, the number of running, sleeping, stopped, and zombie processes. Comparing the number of running processes with the load average helps determine if the system has reached its capacity or perhaps a particular user is running too many processes. The stopped processes should be examined to see if everything is running correctly. The third line of the top output indicates how the CPU time is being divided between the users and the kernel, by displaying the percentage of CPU time used for each. The percentage of user jobs running at a lower priority, niceness-ni, is then listed. Idle mode or ID should be low if the load average is high, and vice versa. The percentage of jobs waiting, WA, for I/O is listed. Interrupts include the percentage of hardware, or HI, versus software interrupts, SI. Steal time, ST, is generally used with virtual machines, which has some of its idle CPU time taken for other uses. The fourth and fifth lines of the top output indicate memory usage, which is divided in two categories. Physical memory, or RAM, displayed on line 4, and swap space, displayed on line 5. Both categories display total memory, used memory, and free space. You need to monitor memory usage very carefully to ensure good system performance. Once the physical memory is exhausted, the system starts using swap space, or temporary storage space on the hard drive, as an extended memory pool. And since accessing disk is much slower than accessing memory, this will negatively affect the system performance. If the system starts using swap often, you can add more swap space. However, adding more physical memory should also be considered. Each line in the process list of the top output displays information about a process. By default, processes are ordered by highest CPU usage. The following information about each process is displayed: process identification number, PID, process owner, the user, priority, PR, and nice values, NI, virtual, physical, and shared memory, status, the S, percentage of CPU and memory used, execution time, the time plus, and command. Besides reporting information, TOP can be utilized interactively for monitoring and controlling processes. While TOP is running in a terminal window, you can enter single-letter commands to change its behavior. For example, you can view the top-ranked processes based on CPU or memory usage. If needed, you can alter the priorities of running processes, or you can stop or kill a process. This table lists what happens when pressing various keys when running TOP.
The top utility is used to interactively monitor what processes and tasks are doing on your system. To start it up, all you have to do is type top. And it will refresh itself at some interval of, I think by default, 2 or 3 seconds. It's easily changed. It shows you standard information about each process, similar to what you get with the PS command, such as the process ID, the user, the priority and niceness, some information about how the memory is being used by the process, the state, SB meaning sleeping, for instance. By default, it is sorted by CPU time, and then there's also memory, the total time, and what the actual command is. The lines at the top have been designed over the years to convey a lot of information. So on the first one, you see how long the system has been up, how many users there are. The load average are rolling averages of how much time has been spent in the last, I believe, 1 minute, 5 minutes, etc. There are currently 295 tasks running on the system, but really only one is running. The others are sleeping. And this shows you the CPU time percentages used by the user processes, by the system, by so-called nice processes, and then idle. And how many would be waiting, how many are high priority, and some other details like that. And then you have basic information about the memory, such how much is being used, how much swap there's available, being used, how much is in cache, etc. If I type the letter 1, I get statistics for each CPU instead of just the amalgamated total, and that can be rather useful. 1 will take it back again. If I hit H, I get a listing of what the possible keys I can hit are and what they do. It wouldn't make sense to try to run through much of that here, but I highly recommend that you run top and play with these different keys and try to understand what kind of information you can extract. Well, top is how you can do it from the command line, and if you hit Q, that will kill the program. You can get similar information by going to your menus and finding System Monitor. And then let me drag that over to this screen. The processes pane on here is pretty much the same as top. It's got the same information. It's easier to do things like resort because I could just click on memory and get it sorted by how much memory is used. If I click again, I'll get it in descending order. Priorities, CPU, etc. You can also, once again, change the priority of processes. You can kill them, etc. So you can do a lot. And if you want to see the graph, just click on resources. You can see what's going with a constantly redrawn graph. And with file systems, you can see how much of your file systems on the computer are actually full, where they're mounted, etc. So that's a brief explanation of top and some related issues.
Suppose you need to perform a task on a specific day sometime in the future. However, you know you will be away from the machine on that day. How will you perform the task? You can use the @utility program to execute any non-interactive command at a specified time, as illustrated in this screenshot. Cron is a time-based scheduling utility program. It can launch routine background jobs at specific times and/or days on an ongoing basis. Cron is driven by a configuration file called the cron table, which contains the various shell commands that need to be run at the properly scheduled times. There are both system-wide cron tab files and individual user-based ones. Each line of the cron tab file represents a job and is composed of a so-called cron expression followed by a shell command to execute. Typing cron tab-e will open the cron tab editor to edit existing jobs or to create new jobs. Each line of the cron tab file will contain 6 fields. And here are some examples. Sometimes a command or job must be delayed or suspended. Suppose, for example, an application has read and processed the contents of a data file and then needs to save a report on a backup system. If the backup system is currently busy or not available, the application can be made to sleep or wait until it can complete its work. Such a delay might be to mount the backup device and prepare it for writing. Sleep suspends execution for at least the specified period of time, which can be given as the number of seconds, the default, minutes, hours, or days. After that time has passed, or an interrupting signal has been received, execution will resume. The syntax is sleep and the number, and then a suffix, where the suffix may be S for seconds, the default, M for minutes, H for hours, or D for days. Sleep and at, or AT, are quite different. Sleep delays execution for a specific period, while at starts execution at a later time. You have completed Chapter 9. Let's summarize the key concepts covered. Processes are used to perform various tasks on the system. Processes can be single-threaded or multi-threaded. Processes can be of different types, such as interactive and non-interactive. Every process has a unique identifier, the PID, to enable the operating system to keep track of it. The nice value, or niceness, can be used to set priority. PS provides information about the currently running processes. You can use top to get constant real-time updates about overall system performance, as well as information about the processes running on the system. Load average indicates the amount of utilization the system is under at particular times. Linux supports background and foreground processing for a job. At executes any non-interactive command at a specified time. Cron is used to schedule tasks that need to be performed at regular intervals. By the end of this chapter, you should be able to explore the file system and its hierarchy, explain the file system architecture, compare files and identify different file types, and backup and compress data. In Linux and all Unix-like operating systems, it is often said everything is a file, or at least it's treated as such. This means whenever you are dealing with normal data files and documents, or with devices such as sound cards and printers, you interact with them through the same kind of input-output operations. This simplifies things. You open a file and perform normal operations like reading the file and writing on it, which is one reason why text editors, which you will learn about in an upcoming section, are so important. On many systems, including Linux, the file system is structured like a tree. The tree is usually portrayed as inverted and starts at what is most often called the root directory, which marks the beginning of the hierarchical file system and is also sometimes referred to as the trunk, or simply denoted by a slash. The root directory is not the same as the root user. The hierarchical file system also contains other elements in the path, or directory names, which are separated by forward slashes, as in user/bin/emacs, where the last element is the actual file name. In this section, you will learn about some basic concepts, including the file system hierarchy, as well as about disk partitions. Linux supports a number of native file system types, expressly created by Linux developers, such as ext3, ext4, squashfs, and btrfs. It also offers implementations of file systems used on other alien operating systems, such as those from Windows, SGI, IBM, or Mac OS. Many older legacy file systems, such as FAT, are also supported. Each file system on a Linux system occupies a disk partition. Partitions help to organize the contents of disks according to the kind and use of the data contained. For example, important programs required to run the system are often kept on a separate partition, known as root or slash. This is a separate partition than the one that contains files owned by regular users of the system, in /home. In addition, temporary files created and destroyed during the normal operation of Linux may be located on dedicated partitions. One advantage of this kind of isolation by type and variability is that when all available space on a particular partition is exhausted, the system may still operate normally. This picture shows the use of the gparted utility, which displays the partition layout on a system which has 4 operating systems on it: RHEL 8, CentOS 7, Ubuntu, and Windows. Before you can start using a file system, you need to mount it on the file system tree at the mount point. This is simply a directory, which may or may not be empty, where the file system is to be grafted on. Sometimes you may need to create the directory if it does not already exist. But keep in mind this warning: if you mount a file system on a non-empty directory, the former contents of that directory are covered up and not accessible until the file system is unmounted. Thus, mount points are usually empty directories. The mount command is used to attach a file system, which can be local to the computer or on a network, somewhere within the file system tree. The basic arguments are the device node and the mount point. For example, sudo mount or /dev/sda5/home will attach the file system contained in the disk partition associated with the /dev/sda5 device node into the file system tree at the /home mount point. There are other ways to specify the partition other than the device node, such as using the disk label or the UUID. To unmount the partition, the command would be sudo umount/home. Note the command is umount, not unmount. Only a root user has the privilege to run these commands, unless the system has been otherwise configured. If you want it to be automatically available every time the system starts up, you need to edit the /etc/fstab accordingly. Looking at this file will show you the configuration of all pre-configured file systems. Man fstab will display how this file is used and how to configure it. Executing mount without any arguments will show all presently mounted file systems. The command df-th disk-free will display information about mounted file systems, including the file system type, and usage statistics about currently used and available space. it's often necessary to share data across physical systems, which may be either in the same location or anywhere that can be reached by the internet. A network, or distributed file system, may have all its data on one machine or have it spread out on more than one network node. A variety of different file systems can be used locally on the individual machines. A network file system can be thought of as a grouping of lower-level file systems of varying types. Many system administrators mount remote users' home directories on a server in order to give them access to the same files and configuration files across multiple client systems. This allows the users to log into different computers, yet still have access to the same files and resources. The most common such file systems is named simply NFS, the network file system. It has a very long history and was first developed by Sun Microsystems. Another common implementation is CIFS, also termed Samba, which has Microsoft roots. In this section, you will learn to identify and differentiate between the most important directories found in Linux. We start with ordinary user's home directory space. Each user has a home directory, usually placed under the /home. The /root directory on modern Linux systems is no more than the home directory of the root user, or superuser, or system administrator account. On multi-user systems, the /home directory infrastructure is often mounted as a separate file system on its own partition, or even exported remotely on a network through NFS. Sometimes you may group users based on their department or function. You can then create subdirectories under the /home directory for each of these groups. For example, a school may organize /home with something like the following: /home/faculty, /home/staff, /home/students. The /bin and /sbin directory. The /bin directory contains executable binaries, essential commands used to boot the system, and essential commands required by all system users, such as cat, cp, ls, mv, ps, and rm. Likewise, the /sbin directory is intended for essential binaries related to system administration, such as fsck and ip. To view a list of these programs, you can type ls/bin/sbin. Commands that are not essential for the system to boot or operate in single-user mode are placed in the /user/bin and /user/sbin directories. Historically, this was done so /user could be mounted as a separate file system that could be mounted at a later stage of system startup or even over a network. However, nowadays, most find this distinction is obsolete. In fact, many distributions have been discovered to be unable to boot with this separation, as this modality had not been used or tested for a long time. Thus, on some of the newest Linux distributions, /user/bin and /bin are actually just symbolically linked together, as are /user/sbin and /sbin. Certain file systems, like the one mounted at /proc, are called pseudo-file systems because they have no permanent presence anywhere on the disk. The /proc file system contains virtual files that only exist in memory, that permit viewing constantly changing kernel data. /proc contains files and directories that mimic kernel structures and configuration information. It does not contain real files, but runtime system information, i.e. system memory, devices mounted, hardware configuration, etc. Some important entries in /proc are the following. /proc has subdirectories as well, including the following. The first example shows there is a directory for every process running on a system, which contains vital information about it. The second example shows a virtual directory that contains a lot of information about the entire system, in particular its hardware and configuration. The /proc file system is very useful because the information it reports is gathered only as needed and never needs storage on the disk. The /dev directory contains device nodes, a type of pseudo-file used by most hardware and software devices, except for network devices. This directory is empty on the disk partition when it's not mounted, and it also contains entries which are created by the udev system, which creates and manages device nodes on Linux, creating them dynamically when devices are found. The /dev directory contains items such as /dev/sda1, the first partition on the first hard disk, /dev/lp1, the second printer, /dev/random, a source of random numbers. The /var directory contains files that are expected to change in size and content as the system is running. var stands for variable, such as the entries in the following directories: system log files, /var/log, and packages and database files like /var/lib, print queues, /var/spool, and temporary files, /var/tmp. The /var directory may be put on its own file system so that growth of the files can be accommodated and any exploding file sizes do not fatally affect the system. Network service directories such as /var/ftp, the FTP service, and /var/www, the HTTP web service, are also found under /var. The /etc directory is the home for system configuration files. It contains no binary programs, although there are some executable scripts. For example, /etc/resolve.conf tells the system where to go on the network to obtain hostname to IP address mappings, DNS. Files like password, shadow, and group for managing user accounts are found in the /etc directory, while some distributions have historically had their own extensive infrastructure under /etc. With the advent of systemd, there is much more uniformity among distributions today. Note that /etc is for system-wide configuration files, and only the superuser can modify files there. User-specific configuration files are always found under their home directory. The /boot directory contains the few essential files needed to boot the system. For every alternative kernel installed on the system, there are these 4 files. vm-linuz, which is the compressed Linux kernel required for booting. init ram-fs, which is the initial RAM file system required for booting, sometimes called init-rd, not init ram-fs. And then config, the kernel configuration file, only used for debugging and bookkeeping. And finally, system.map, which is the kernel symbol table only used for debugging. Each of these files has a kernel version appended to its name. The grub files, such as boot/grub/grub.conf or /boot/grub2/grub2cfg, are also found under the /boot directory. This screenshot shows an example listing of the /boot directory taken from the RHEL system that has multiple installed kernels, including both distribution-supplied and custom-compiled ones. Names will vary and things will tend to look somewhat different on a different distribution. /lib contains libraries, which are common code shared by applications and needed for them to run. It contains libraries for essential programs in /bin and /sbin. These library file names either start with ld or lib. Here's an example. Most of these are what is known as dynamically loaded libraries, also known as shared libraries or shared objects. On some Linux distributions, there exists a /lib64 directory containing 64-bit libraries, while /lib contains 32-bit versions. On recent Linux distributions, you can find this. Just like for /bin and /sbin, the directories just point to those under /user. Kernel modules, or kernel code, often device drivers that can be loaded and unloaded without restarting the system, are located in /lib/modules/ and then the kernel version number. One often uses removable media such as USB drives, CDs, and DVDs to make the material accessible through the regular file system. It has to be mounted at a convenient location. Most Linux systems are configured so any removable media are automatically mounted when the system notices something has been plugged in. While historically this was done under the /media directory, modern Linux distributions place these mount points under the /run directory. For example, a USB pen drive with a label My USB Drive for a user named student will be mounted at /run/media/student/My USB Drive. The /mount directory has been used since the early days of Unix for temporarily mounting file systems. These can be those on removable media, but more often they might be network file systems, which are not normally mounted. Or these can be temporary partitions or so-called loopback file systems, which are files which pretend to be partitions. Here are some additional directories to be found under the root directory. The /user directory tree contains theoretically non-essential programs and scripts, in the sense that they should not be needed to initially boot the system, and has at least the following subdirectories shown here. Now that you know about the file system and its structure, let's learn how to manage files and directories. Diff is used to compare files and directories. This often used utility program has many useful options, including the ones you see here. To compare two files at the command prompt, type diff in the options, file name 1, file name 2. Diff is meant to be used for text files. For binary files, one can use CMP. In this section, you will learn additional methods for comparing files and how to apply patches to files. You can compare 3 files at once using diff3, which uses one file as the reference basis for the other 2. For example, suppose you and a coworker both have made modifications to the same file working at the same time, independently. Diff3 can show the differences based on the common file you both started with. Here's the syntax for diff3. And this graphic shows the use of diff3. Many modifications to source code and configuration files are distributed utilizing patches, which are applied, not surprisingly, with the patch program. A patch file contains the deltas, or changes, required to update an older version of a file to the new one. The patch files are actually produced by running diff with the correct options, as in this command. Distributing just the patch is more concise and efficient than distributing the entire file. For example, if only one line needs to change in a file that contains 1,000 lines, the patch file will be just a few lines long. To apply a patch, you can just do either of these two methods. The first usage is more common, as it's often used to apply changes to an entire directory tree rather than just one file, as in the second example. To understand the use of the -P1 option and many others, see the man page for patch. In Linux, a file's extension often does not categorize it the way it might in other operating systems. One cannot assume that a file named file.txt is a text file and not an executable program. In Linux, a file name is generally more meaningful to the user of the system than the system itself. In fact, most applications directly examine a file's contents to see what kind of app object it is, rather than relying on an extension. This is very different from the way Windows handles file names, where a file name ending in .exe, for example, represents an executable binary file. The real nature of a file can be determined by using the file utility. For the file names given as arguments, it examines the contents and certain characteristics to determine whether the files are plain text, shared libraries, executable programs, scripts, or something else. There are many ways you can back up data or even your entire system. Basic ways to do so include the use of simple copying with CP and use of the more robust rsync. Both can be used to synchronize entire directory trees. However, rsync is more efficient because it checks if the file being copied already exists. If the file exists and there is no change in size or modification time, rsync will avoid an unnecessary copy and save time. Furthermore, because rsync copies only the parts of the file that have actually changed, it can be very fast. CP can only copy files to and from destinations on the local machine. But rsync can also be used to copy files from one machine to another. Locations are designated in the target:path form, where target can be the form of someone at host, and the someone at part is optional and used if the remote user is different from the local user. Rsync is very efficient when recursively copying one directory tree to another, because only the differences are transmitted over the network. One often synchronizes the destination directory tree with the origin using the -r option to recursively walk down the directory tree, copying all files and directories below the one listed as the source. rsync is a very powerful utility. For example, a very useful way to back up a project directory might be to use this command. Note that rsync can be very destructive. Accidental misuse can do a lot of harm to data and programs by inadvertently copying changes to where they are not wanted. Take care to specify the correct options and paths. It's highly recommended that you first test your rsync command using the -try-run option to ensure that it provides the results that you want. To use rsync at the command prompt, type rsync source file, destination file, where either file can be on the local machine or on a network machine. The contents of source file will be copied to destination file. A good combination of options is shown here. The file data is often compressed to save disk space and reduce the time it takes to transmit files over networks. Linux uses a number of methods to perform this compression, including these. These techniques vary in the efficiency of the compression, or how much space is saved, and in how long they take to compress. Generally, the more efficient techniques take longer. Decompression time does not vary as much across different methods. You have completed Chapter 10. Let's summarize the key concepts covered. The file system tree starts at what is often called the root directory, or trunk, or /. The File System Hierarchical Standard, FHS, provides Linux developers and system administrators a standard directory structure for the file system. Partitions help to segregate files according to usage, ownership, and type. File systems can be mounted anywhere on the main file system tree at a mount point. Automatic file systems mounting can be set up by editing etc/fstab. NFS, or network file system, is a useful method for sharing files and data through the network systems. File systems like /proc are called pseudo file systems because they exist only in memory. /root is the home directory for the root user. /var may be put in its own file system so that growth can be contained and not fatally affect the system. /boot contains the basic files needed to boot the system. Patch is a very useful tool in Linux. Many modifications to source code and configuration files are distributed with patch files, as they contain the deltas or changes to go from an old version of a file to the new version of a file. File extensions in Linux do not necessarily mean that a file is of a certain type. CP is used to copy files on the local machine, while rsync can be used to copy files from one machine to another, as well as synchronize contents. By the end of this chapter, you should be familiar with how to create and edit files using the available Linux text editors, Nano, a simple text-based editor, gedit, a simple graphical editor, VI and Emacs, two advanced editors with both text-based and graphical interfaces. At some point, you will need to manually edit text files. You might be composing an email offline, writing a script to be used for Bash or other command interpreters, altering a system or application configuration file, or developing source code for a programming language such as C, Python, or Java. Linux administrators may sidestep using a text editor, instead employing graphical utilities for creating and modifying system configuration files. However, this can be more laborious than directly using a text editor and be more limited in capability. Note that word processing applications, including those that are part of common Office application suites, are not really basic text editors. They add a lot of extra, usually invisible formatting information that will probably render system administration configuration files unusable for their intended purpose. So, knowing how to confidently use one or more text editors is really an essential skill to have for Linux. By now, you have certainly realized Linux is packed with choices. When it comes to text editors, there are many choices, ranging from quite simple to very complex, including Nano, gedit, vi, or Emacs. In this section, we learn first about the Nano and gedit editors, which are relatively simple and easy to learn, and then later, the more complicated choices, vi and Emacs. Before we start, let's take a look at some cases where an editor is not needed. Sometimes you may want to create a short file and don't want to bother invoking a full text editor. In addition, doing so can be quite useful when used from within scripts, even when creating longer files. You'll no doubt find yourself using this method when you start on the later chapters that cover shell scripting. If you want to create a file without using an editor, there are two standard ways to create one from the command line and fill it with content. The first one is to use echo repeatedly, like shown here. Note that while a single greater than sign will send the output of a command to a file, two of them will append the new output to an existing file. The second way is to use cat combined with redirection, as in this example here. Both techniques produce a file with the following lines in it: line 1, line 2, line 3, and are extremely useful when employed by scripts. There are some text editors that are pretty obvious. They require no particular experience to learn and are actually quite capable, even robust. A particularly easy to use one is the text terminal-based editor, Nano. Just invoke Nano by giving a file name as an argument. All the help you need is displayed at the bottom of the screen, and you should be able to proceed without any problem. As a graphical editor, gedit is part of the GNOME desktop system. kwrite is associated with KDE. The gedit and kwrite editors are very easy to use and are extremely capable. They're also very configurable. They look a lot like Notepad in Windows. Other variants, such as Kate, are also supported by KDE. Nano is easy to use and requires very little effort to learn. To open a file, type nano and then the file name, and press enter. If the file does not exist, it will be created. Nano provides a two-line shortcut at the bottom of the screen that lists the available commands. Some of these commands are Ctrl-G, display the help screen, Ctrl-O, write to a file, Ctrl-X, exit a file, Ctrl-R, insert contents from another file to the current buffer, or Ctrl-C, show the cursor position. gedit is a simple-to-use graphical editor that can only be run within a graphical desktop environment. It is visually quite similar to the Notepad text editor in Windows, but it's actually far more capable and very configurable, and has a wealth of plugins available to extend its capabilities further. To open a new file, find the program in your desktop's menu system, or from the command line type gedit and then the file name. If the file does not exist, it will be created. Using gedit is pretty straightforward and does not require much training. Its interface is composed of quite familiar elements. Developers and administrators experienced in working on Unix-like systems almost always use one of the two venerable editing options, VI and Emacs. Both are present or easily available on all distributions and are completely compatible with the versions available on other operating systems. Both VI and Emacs have a basic, purely text-based form that can run in a non-graphical environment. They also have one or more graphical interface forms with extended capabilities. These may be friendlier for a less experienced user. While VI and Emacs can have significantly steep learning curves for new users, they are extremely efficient when one has learned how to use them. Usually the actual program installed on your system is Vim, which stands for VI Improved, and is aliased to the name VI. Even if you don't want to use VI, it's good to gain some familiarity with it. It's a standard tool installed on virtually all Linux distributions and Mac OS. Indeed, there may be times when there is no other editor available on the system. And remember, VI and Vim are going to be very similar. GNOME extends VI with a graphical interface known as gvim, and KDE offers kvim. Either of these may be easier to use at first. When using VI, All commands are entered through the keyboard. You don't need to keep moving your hands to use a pointer device, such as a mouse or touchpad, unless you want to do so when using one of the graphical versions of the editor. Typing Vim Tutor launches a short but very comprehensive tutorial for those who want to learn their first VI commands. Even though it provides only an introduction and just 7 lessons, it has enough material to make you a very proficient VI user because it covers a large number of commands. After learning these basic ones, you can look up new tricks to incorporate into your list of VI commands because there are always more optimal ways to do things in VI with less typing. VI provides 3 modes, as described in this table here. It's vital to not lose track of which mode you're in. Many keystrokes and commands behave quite differently in different modes. This table describes the most important commands used to start, exit, read, and write files in VI. The Enter key needs to be pressed after all of these commands. And this table describes the most important keystrokes used when changing cursor positions in VI. Line mode commands, those following a colon, require the Enter key to be pressed after the command is typed.
Let's get started on using modes and cursor movements in VI. Open VI by typing VI followed by the file name. VI opens in command mode. Type I to enter insert mode. VI's insert mode is displayed. Type the following sentences. The quick brown fox jumped over the lazy dog. Nobody expects the Spanish Inquisition. To exit insert mode and switch to command mode, press Escape. To exit VI and save the file, type :WQ and press Enter. Open the recently saved file and place the cursor on the letter K in the word quick in the first sentence. To move the cursor 4 characters to the left, type H 4 times. The cursor is moved to letter Q of the word quick. To move the cursor to the next line, type J. To move the cursor to the beginning of the next word, type W. The cursor is moved to the beginning of the word expects. To move the cursor to the end, type the $sign. The cursor is moved to the end of the second sentence. Type I to enter insert mode. VI insert mode is displayed. To insert text at the end of the second sentence, type A and type history. The word history is displayed to the end of the sentence. To exit insert mode and switch to command mode, press Escape. To exit VI and save the file, type :WQ and press Enter.
Here you can see the most important commands used when searching for text in VI. The Enter key should be pressed after typing the search pattern. This table describes the most important keystrokes used when searching for text in VI. And this table describes the most important keystrokes used when changing, adding, and deleting text in VI. Typing the sh command opens an external command shell. When you exit the shell, you will resume your editing session. Typing ! executes a command from within VI. The command follows the exclamation point. This technique is best suited for non-interactive commands, such as $WC%. Typing this will run the word count command on the file. The character the percentage represents the file currently being edited.
Let's get started on using external commands, saving and closing in Vim Editor. Open VI Editor by typing VI followed by the file name. VI opens in command mode. Type I to enter insert mode. VI's insert mode is displayed. Type the following sentences. Nobody expects the Spanish Inquisition. Nobody expects the 2020 revolution. To exit insert mode and switch to command mode, press Escape. To write and quit the file, type :WQ. The file is updated with the changes and closed. Open VI by typing VI followed by the file name. To count the words in the current file, type : exclamation, WC, %. The word count is displayed. Press Enter to continue editing. To quit if no edits were made in the file, type :Q. The file is closed. Open VI by typing VI followed by file name. To quit without saving the file, type :Q! The file is closed without saving the changes.
The Emacs editor is a popular competitor for VI. Unlike VI, it does not work with modes. Emacs is highly customizable and includes a large number of features. It was initially designed for use on a console, but was soon adopted to work with a GUI as well. Emacs has many other capabilities other than simple text editing. For example, it can be used for email, debugging, and many other things. Rather than having different modes for command and insert like VI, Emacs uses the control and meta or alt or escape keys for special commands. Here you can see some of the most important key combinations that are used when starting, exiting, reading, and writing files in Emacs. The Emacs tutorial is a good place to start learning basic commands. It's available anytime when in Emacs by simply typing Control-H for help, and then the letter T for tutorial.
We will now demonstrate some of the operations you can do with Emacs in your daily work. So first, let's get a file to edit. So working in the TMP directory, let's get a copy of etc. password and bring it over here. And then in order to work on it, I just have to say Emacs pass and the name of the file. Now the default font here is a little small, so I'll play a trick and hit Control and the middle button of the mouse to control the size of the font. And then I'll make the window a little bigger. Okay, so we've done that. Now, suppose I want to look for a certain string, let's say FTP. I would hit Control-S and type in the very bottom window, the very bottom line here, FTP, so you can see down here. And you'll see it brought me to FTP. I'll go back to the beginning of the line by hitting Control-A. And then let's say I want to change all occurrences of the string FTP to something else. I hit Escape, %, and then I'll say FTP again on the bottom line. And then let's just do it backwards in capitals, PTF. And you see I hit space, it does the first one. Space, it does the second one. Space, it does the third one. If I had hit an exclamation point, it would have done all of them in the entire file. Suppose I want to remove a line, I can just hit Control-K, and it's gone. Control-K is gone again. Suppose I want to remove a range of lines, I hit Control space, and then I go down a few lines with either the arrow key or Control-N. I hit Control-W, and they're gone. If I want to move them further on in the file, I go down a few lines and I hit Control-Y for yank, and they're back in there. One nice thing I can do with Emacs is open up multiple windows at the same time. So let me hit Control-X, 2, and now I've got 2 windows. And I can switch to the bottom window by hitting Control-X-O for other. And then I hit Control-X-F, I can put a different file in that buffer. So let's say I put in etc group. Okay, and once again I'll make the font a little bigger by hitting Control and the middle button on the mouse. Okay, and you'll notice the bottom line is actually write protected, so I can't really delete anything because it belongs to root. If I try to delete this line, it won't let me do it. It says buffer is read only. But in general, like if I had 2 files with the same permissions, I could cut and paste and go from one to the other. To get back to just one, I can do Control-X1, and I have only this, but if I really wanted the other window, I can hit Control-XB, and I'm back in the password file. If I want to rewrite it, I can hit Control-XW, Control-X, Control-W, and that would let me write it as a different name, so I'll say PASWD revised, and it's there. If I want to terminate the program, I say Control-XS to make sure things have been saved, and then Control-XC. and I'm done. So you can see we use the control key quite a bit in Emacs. The position most keyboards put it in these days is a little unnatural, all the way at the bottom left or right. So veteran Emacs users tend to remap the keyboard so that the caps lock key also works as control. So that's some of the basic operations you would do in day-to-day use of Emacs.
You have completed Chapter 11. Let's summarize the key concepts covered. Text editors, rather than word processing programs, are used quite often in Linux for tasks such as creating or modifying system configuration files, writing scripts, developing source code, and more. Nano is an easy-to-use text-based editor that utilizes on-screen prompts. gedit is a graphical editor very similar to Notepad in Windows. The VI editor is available on all Linux systems and is very widely used. Graphical extension versions of VI are widely available as well. Emacs is available on all Linux systems as a popular alternative to VI. Emacs can support both a graphical user interface and a text mode interface. To access the VI tutorial, type vim tutor at a command line window. To access the Emacs tutorial, type Ctrl-H and then T from within Emacs. VI has 3 modes: command, insert, and line. Emacs has only one, but requires use of special keys such as Control and Escape. Both editors use various combinations of keystrokes to accomplish tasks. The learning curve to master these can be long, but once mastered, using either editor is extremely efficient. By the end of this chapter, you should be able to use and configure user accounts and user groups, use and set environment variables, use the previous shell command history, use keyboard shortcuts, use and define aliases, use and set file permissions and ownership. As you know, Linux is a multi-user operating system, meaning more than one user can log on at the same time. To identify the current user, type "Who am I?" To list the currently logged on users, type "Who." Giving "Who" the "-a" option will give more detailed information. In Linux, the command shell program, generally bash, uses one or more startup files to configure the user environment. Files in the /etc directory define global settings for all users, while initialization files in the user's home directory can include and/or override the global settings. The startup files can do anything the user would like to do in every command shell, such as customizing the prompt, defining command line shortcuts and aliases, setting the default text editor, setting the path for where to find executable programs. The standard prescription is that when you first log into Linux, /etc/profile is read and evaluated, after which the following files are searched, if they exist, in this order: .bash profile, .bash login, .profile, where the squiggly line /dot denotes the user's home directory. The Linux login shell evaluates whatever startup file that it comes across first and ignores the rest. This means that if it finds .bash profile, it ignores .bash login and .profile. Different distributions may use different startup files. However, every time you create a new shell or terminal window, you do not have to perform a full system login. Only a file name .bashrc file is read and evaluated. Although this file is not read and evaluated along with the login shell, most distributions and/or users include the .bashrc file from within one of the 3 user-owned startup files. Most commonly, users only fiddle with the .bashrc as it is invoked every time a new command line shell initiates, or another program is launched from a terminal window, while the other files are read and executed only when the user first logs on to the system. Recent distributions sometimes do not even have bash profile and/or bash login, and some just do little more than include .bashrc. You can create customized commands or modify the behavior of already existing ones by creating aliases. Most often, these aliases are placed in your bashrc file, so they're available to any command shells you create. Unalias removes an alias. Typing alias with no argument will list currently defined aliases. Please note that there should not be any spaces on either side of the equal sign, and the alias definition needs to be placed within either single or double quotes if it contains any spaces. All Linux users are assigned a unique user ID, UID, which is just an integer. Normal users start with a UID of 1000 or greater. Linux uses groups for organizing users. Groups are collections of accounts with certain shared permissions. Control of group membership is administered through the /etc/group file, which shows a list of groups and their members. By default, every user belongs to a default or primary group. When a user logs in, the group membership is set for their primary group, and all the members enjoy the same level of access and privilege. Permissions on various files and directories can be modified at the group level. Users also have one or more group IDs, GID, including a default one which is the same as the user ID. These numbers are associated with names through the files, /etc/password and /etc/group. Groups are used to establish a set of users who have common interests for the purpose of access rights, privileges, and security considerations. Access rights to files and devices are granted on the basis of the user and the group they belong to. Distributions have straightforward graphical interfaces for creating and removing users and groups, and manipulating group membership. However, it's often useful to do it from the command line or from within shell scripts. Only the root user can add and remove users and groups. Adding a new user is done with user_add, and removing an existing user is done with user_del. In the simplest form, an account for the new user bjmoose would be done with sudo user_add bjmoose, which by default sets the home directory to /home/bjmoose, populates it with some basic files, copied from /etc/skel, and adds a line to the /etc/password, such as this, and sets the default shell to /bin/bash. Removing a user account is as easy as typing user_del bjmoose. However, this will leave the /home/bjmoose directory intact. This might be useful if it's a temporary inactivation. To remove the home directory while removing the account, one needs to use the -r option to user_del. Typing ID with no arguments gives information about the current user, as in this ID. If given the name of another user as an argument, ID will report information about that other user.
Let's get some experience with creating, modifying, and removing a new user account. We will do this on Ubuntu 17.04. There are some variations between distributions about what exactly is created when a new account is created and exactly which files are there, etc. This is mostly controlled by a file under etc. default user_add appropriately named. So you can see, for example, in here, the default shell is set to be shell bsh, bin_sh. Now, on some distributions, such as Red Hat, this file is rather short and not very well documented. On Ubuntu, it's rather long. So let's create the account. So sudo user_add, and I'll say -m to make sure it creates a home directory. Some distributions do not do that by default. Ubuntu does not, for instance, and neither does OpenSUSE. I'll give the full name to be Eric Dolphy. I'll specify the default shell to be bin_bash with the S option. And here's the name edolphy, edolphy. Now I still have to specify a password, so I'll do that with sudo passwd edolphy, and then I type something, and now the account exists. And I can verify that by making sure entries were made in the etcy password file and etcy group. And there we go. Notice it is now user 1001. Remember, normal users start at 1000 and student is user 1000. And so that's appropriate. And also the other information I specified is there, such as the full username and the shell bin bash. And the group is set to be 1001, which is the same ID as the user. All users are created with at least one group that has the same number as their username. Now let's actually try to log into that account, and I'll do that with SSH and EDOLPHY at localhost. And I'll give the password. And I succeeded just fine. So let's see what's actually in that directory. And you'll see there isn't much, but these are files that all new users get. And let me log out now. And that's controlled by whatever's in the etc skel directory. Anything you put in there, let me do the A option. Anything you put in there will show up in any new user's account. So let's just clean up, and I'll do that with user del-r edolphi. And the R is necessary to make sure it removes the home directory. You notice I get a warning message about not having created a mail spool file. That's harmless. And if I do ls-l on home now, we see the account is gone. So we're all cleaned up.
Adding a new group is done with group add. So you can use sudo /user/sbin/group add a new group. The group can be removed with sudo /user/sbin/group del a new group. Adding a user to an already existing group is done with user mod. For example, when you would first look at what groups the user already belongs to, and then add the new group. Sudo /user/sbin/user-mod -a-g a new group RJ Squirrel. And then groups RJ Squirrel will show the new group. These utilities update the /etc/group as necessary. Make sure you use the -a option for append so as to avoid removing already existing groups. Group mod can be used to change group properties, such as the group ID with the -g option or its name with the -in option. Removing a user from the group is somewhat trickier. The -g option to user mod must give a complete list of groups. Thus, if you do sudo /user/sbin/user-mod -g RJ Squirrel, and then do groups RJ Squirrel, you'll see that only the RJ Squirrel group will be left. The root account is very powerful and has full access to the system. Other operating systems often call this the administrator account. In Linux, it's often called the superuser account. You must be extremely cautious before granting full root access to a user. It's rarely, if ever, justified. External attacks often consist of tricks used to elevate the root account. However, you can use sudo to assign more limited privileges to user accounts, but only do it on a temporary basis and only for a specific subset of commands. When assigning elevated privileges, you can use the command su, a switch or substitute user, to launch a new shell running as another user. You must type the password of the user you are becoming. Most often, this other user is root, and the new shell allows the use of elevated privileges until it is executed. It's almost always a bad practice to use su to become root. Resulting errors can include deletion of vital files from the system and security breaches. Granting privileges using sudo is less dangerous and is preferred. By default, sudo must be enabled on a per-user basis. However, some distributions, such as Ubuntu, enable it by default for at least one main user or give this as an installation option. To temporarily become the superuser for a series of commands, you can type su and then be prompted for the root password. To execute just one command with root privileges, type sudo and then the command. When the command is complete, you will return to being a normal unprivileged user. Sudo configuration files are stored in the /etc/sudoers file and in the /etc/sudoers.d directory. By default, the sudoers.d directory is empty. And whenever you talk about sudo in a course or article, you're basically required to show this webcomic by XKCD. Environment variables are quantities that have specific values which may be utilized by the command shell, such as bash or other utilities and applications. Some environment variables are given preset values by the system, which can usually be overridden, while others are set directly by the user, either at the command line or within startup and other scripts. An environment variable is actually just a character string that contains information used by one or more applications. There are a number of ways to view the values of currently set environment variables. One can type set, env, or export. Depending on the state of your system, set may print out many more lines than the other two methods. By default, variables created within a script are only available to the current shell. Child processes, subshells, will not have access to values that have been set or modified. Allowing child processes to see the values requires use of the export command. You can also set environment variables to be fed as a one-shot to a command, as in the following. This feeds the values of the sdrs and kroot environment variables to the command make modules install. Home is an environment variable that represents the home or login directory of the user. cd without arguments will change the current working directory to the value of home. Note the tilde character is often used as an abbreviation for home. Thus, cd home and cd with the tilde are completely equivalent statements. Path is an ordered list of directories. The path, which is scanned when a command is given to find the appropriate program or script to run. Each directory in the path is separated by colons. A null, or empty directory name, or slash, indicates the current directory at any given time. So in this example, there is a null directory before the first colon. Similarly, for this, there is a null directory between path 1 and path 2. To prefix a private bin directory to your path, you can use this command. The environment variable shell points to the user's default command shell, the program that is handling whatever you type in a command window, usually bash, and it contains the full path name to the shell. Prompt statement, or PS, is used to customize your prompt string in your terminal windows to display the information you want. PS1 is the primary prompt variable, which controls what your command line prompt looks like. The following special characters can be included in PS1. They must be surrounded in single quotes when they are used, as in this example. Bash keeps track of previously entered commands and statements in a history buffer. You can recall previously used commands simply by using the up and down cursor keys. To view the list of previously executed commands, you can just type history at the command line. This list of commands is displayed with the most recent command appearing last in the list. This information is stored in the /bash history. If you have multiple terminals open, the commands typed in each session are not saved until the session terminates. Several associated environment variables can be used to get information about the history file. Hist file is the location of the history file. Hist file size is the maximum number of lines in the history file, default 500. Hist size is the maximum number of commands in the history file. Hist control is how commands are stored. Hist ignore is which command lines can be unsaved. For a complete description of the use of these environment variables, see the man page in Bash. There are specific keys to perform various tasks. If you want to recall a command in the history list, but do not want to press the arrow key repeatedly, you can press Ctrl-R to do a reverse intelligent search. As you start typing, the search goes back in reverse order to the first command that matches the letters you have typed. By typing more successive letters, you make the match more and more specific. You can use keyboard shortcuts to perform different tasks quickly. This table lists some of these keyboard shortcuts and their uses. Note the case of the hotkey does not matter, meaning doing Ctrl-A is the same as doing Ctrl-A. In Linux and other Unix-based operating systems, every file is associated with a user who is the owner. Every file is also associated with a group, a subset of all users, which has an interest in the file and certain rights or permissions: read, write, and execute. The following utility programs involve user and group ownership and permission settings. Files have three kinds of permissions: read, write, and execute. These are generally represented as the RWX. These permissions affect the three groups of owners: user owner, group, and others. As a result, you have the following three groups of three permissions. There are a number of different ways to use chmod. For instance, to give the owner and others execute permission and remove the group write permission, you can do this, where the U stands for user or owner, O stands for other, world, and G stands for group. This kind of syntax can be difficult to type and remember, so one often uses a shorthand which lets you set all the permissions in one step. This is done with a simple algorithm, and a single digit suffices to specify all three permission bits for each entity. This digit is the sum of 4 if read permission is desired, 2 if write permission is desired, 1 if execute permission is desired. So 7 means read, write, execute, 6 means read, write, 5 means read, execute. When you apply this to the chmod command, you have to give 3 digits for each degree of freedom, such as chmod 755 some file. Now let's see an example of changing file ownership using chown, as shown in this screenshot. First, we create 2 empty files using touch. Notice it requires sudo to change the owner of file 2 to root. The second chown command changes both owner and group at the same time. Finally, only the super user can remove the files. Now let's see an example of changing the group ownership using chgrp. You have completed Chapter 12. Let's summarize the key concepts covered. Linux is a multi-user system. To find the currently logged on users, you can use the who command. To find the current user ID, you can use the whoami command. The root account has full access to the system. It's never sensible to grant full root access to a user. You can assign root privileges to regular user accounts on a temporary basis using the sudo command. The shell program, or bash, uses multiple startup files to create the user environment. Each file affects the interactive environment in a different way. /etc/profile provides the global settings. Advantages of startup files include that they customize the user's prompt, set the user's terminal type, set the command line shortcuts and aliases, and set the default text editor. An environment variable is a character string that contains data used by one or more applications. The built-in shell variables can be customized to suit your requirements. The history command recalls a list of previous commands, which can be edited and recycled. In Linux, various keyboard shortcuts can be used at the command prompt instead of long actual commands. You can customize commands by creating aliases. Adding an alias to the /.bashrc file will make it available for other shells. File permissions can be changed by typing chmod permissions in the file name. File ownership is changed by typing chown, then the owner, and the file name. File group ownership is changed by typing chgrp, then the group, then the file name. By the end of this chapter, you should be able to display and append to file contents using cat and echo, edit and print file contents using sed and awk, search for patterns using grep, use multiple other utilities for file and text manipulation. Irrespective of the role you play with Linux, such as system administrator, developer, or user, you often need to browse through and parse text files and/or extract data from them. These are file manipulation operations. Thus, it's essential for the Linux user to become adept at performing certain operations on files. Most of the time, such file manipulation is done at the command line, which allows users to perform tasks more efficiently than while using a GUI. Furthermore, the command line is more suitable for automating often executed tasks. Indeed, experienced system administrators write customized scripts to accomplish such repetitive tasks, standardized for each particular environment. We'll discuss such scripting later in much detail. In this section, we'll concentrate on command line file and text manipulation related utilities. Cat is short for concatenate and is one of the most frequently used Linux command line utilities. It's often used to read and print files, as well as for simply viewing file contents. To view a file, use the following command: cat and then the file name. For example, cat readme.txt will display the contents of readme.txt on the terminal. However, the main purpose of cat is often to combine or concatenate multiple files together. You can perform the actions listed in this table using cat. The tac command, or cat spelled backwards, prints the lines of a file in reverse order. Each line remains the same, but the order of lines is inverted. The syntax of tac is exactly the same as for cat, as in the following. Cat can be used to read from standard input, such as the terminal window, if no files are specified. You can use the greater than operator to create and add new lines to a file, and the double greater than operator to append lines or files to an existing file. To create a new file at the command prompt, type cat greater than file name and press the enter key. This command creates a new file and waits for the user to edit or enter the text. After you finish typing the required text, press Ctrl D at the beginning of the next line to save and exit the editing.
Let's demonstrate some of the basic operations you can perform with the cat utility, where the word cat stands for concatenate. It's typically used to copy files, combine them, etc. So first we will need a couple of simple text files to play with. Let's create one using a text editor. Let's say nano, so nano file1.txt. And I will just type in a couple of lines, actually 3 lines, with a blank one at the end. I hit Control X for exit. I say yes, I want to save the modified buffer, and I keep the name. So now I can look at the file created with cat. So I do cat file1.txt. Perfect. Now let's create another one interactively using cat itself, as we talked about earlier. So I can say cat in direction with EOF, and I'll put it into file2.txt. Here is a second file with a few lines. And then I just type EOF on a line. And that closes the input phase. And I can say cat file2.txt. It's there. If I want to see them both together, I can say cat file1.txt, file2.txt. I see it combined, or I could send it into a third file, file3.txt. And then clear the screen, I can say cat file3.txt, and I see the combined two files in a third file. So this is how you use cat. It's an everyday operation. You rarely do anything that much more complicated with it.
System administrators need to work with configuration files, text files, documentation files, and log files. Some of these files may be larger or become quite large as they accumulate data with time. These files will require both viewing and administrative updating. In this section, you will learn how to manage such large files. For example, a banking system might maintain one simple large log file to record details of all of one day's ATM transactions. Due to a security attack or a malfunction, the administrator might be forced to check for some data by navigating within the file. In such cases, directly opening the file in an editor will cause issues due to high memory utilization, as an editor will usually try to read the whole file into memory first. However, one can use less to view the contents of such a large file, scrolling up and down page by page without the system having to place the entire file in memory before starting. This is much faster than using a text editor. Viewing some file can be done by typing either of the two following commands: less some file or cat some file, pipe less. By default, man pages are sent through the less command. You may have encountered the older more utility, which has some basic functionality but fewer capabilities, i.e. less is more. Head reads the first few lines of each named file, 10 by default, and displays it on standard output. You can give a different number of lines in an option. For example, if you want to print the first 5 lines from etc/default/grub, we can use this command, head-in, and then etc/default/grub. You can also just do this, head-5 etc/default/grub. Tail prints the last few lines of each named file and displays it on standard output. By default, it displays the last 10 lines. You can give a different number of lines as an option. Tail is especially useful when you are troubleshooting any issue using log files, as you probably want to see the most recent lines of output. For example, to display the last 15 lines of sumfile.log, we can use this command, tail-in 15 sumfile.log. You can also just do this, tail-15 sumfile.log. To continually monitor new output in a growing log file, we can do tail-f sumfile.log. This command will continuously display any new lines of output in sumfile.log as soon as they appear. Thus, it enables you to monitor any current activity that is being reported and recorded. It's very common to create and then repeatedly edit and/or extract contents from a file. Let's learn how to use SED and AWK to easily perform such operations. Note that many Linux users and administrators will write scripts using comprehensive scripting languages, such as Python and Perl, rather than use SED and AWK, and some of the other utilities we'll discuss later. Using such utilities is certainly fine in most circumstances. One should always feel free to use the tools one is experienced with. However, the utilities that are described here are much lighter, i.e. they use fewer system resources and execute faster. There are situations, such as during booting the system, where a lot of time would be wasted using the more complicated tools, and the system may not even be able to run them. So the simpler tools will always be needed. SED is a powerful text processing tool and is one of the oldest, earliest, and most powerful Unix utilities. It's used to modify the contents of a file or input stream, usually placing the contents into a new file or output stream. Its name is an abbreviation for stream editor. SED can filter text as well as perform substitutions in data streams. Data from an input source or file is taken and moved to a working space. The entire list of operations or modifications is applied over the data in the working space, and then final contents are moved to the standard output space or stream. You can invoke SED or SED using commands like those listed in this table. The -E option allows you to specify multiple editing commands simultaneously at the command line. It's unnecessary if you only have one operation invoked. Now that you know that you can perform multiple editing and filtering operations with SED, let's explain some of them in more detail. The table explains some basic operations where pattern is the current string and replace_string is the new string.
Let's demonstrate some of the most elementary operations you can perform with SED on a Fedora system. So I have taken the liberty to prepare a simple text file before we start, which looks like this, cat infile.txt. It just says 3 lines indicating their presence. Suppose I do SED-E/ and then let's say is to R on the file, and the output will go right on standard out. And you see it changed only the first instance on every line, so I even have var instead of this. I can make a slight modification to the command if I put a G at the end of it. And you see this time it caught every instance. I could also do something like this, 1,2s, and it only did it on the first and the second line, but it left the third line alone. You notice that I don't have to use a // I can use many other characters, so here I'll use a colon. And it makes no difference what I use. Now there is an option for SED to change character streams in place on the original file, but it's a pretty dangerous operation to do since you destroy the original file. So generally it's better to send the output into another file, so I'll call that one outfile.txt. Oh, I forgot to say infile.txt for input. So it hung. So now I can look at outfile.txt. You see, and that's the output. And if I want to use the diff command to see the difference, I can do something like this. Diff infile.txt, outfile.txt. And it shows me the 2 lines that have changed. Now you can do some pretty complicated things with SED when you're trying to deal with special characters, including spaces and question marks and stars. Life can get pretty complicated. It respects everything in the world about what are called regular expressions, which can look rather strange. But it's a daily tool that system administrators do to make elementary substitutions in files. So that's a little bit about SED.
AWK or awk is used to extract and then print specific contents of a file and is often used to construct reports. It was created at Bell Labs in the 1970s and derived its name from the last names of its authors. Awk has the following features. It's a powerful utility and interpreted programming language. It's used to manipulate data files and for retrieving and processing text. It works well with fields, containing a single piece of data, essentially a column, and records, a collection of fields, essentially a line in a file. Awk is invoked as shown in this example. As was said, short awk commands can be specified directly at the command line, but a more complex script can be saved in a file that you can specify using the -F option. This table explains the basic tasks that can be performed using awk. The input file is read one line at a time, and for each line, awk matches the given pattern in the given order and performs the requested action. The -f option allows you to specify a particular field separator character. For example, the /etc/password file uses a colon to separate the fields. So the -f option is used with the /etc/password file. The command or action in awk needs to be surrounded with apostrophes or single quotes. Awk can be used like the following, like in this example. In managing your files, you may need to perform tasks such as sorting data and copying data from one location to another. Linux provides numerous file manipulation utilities that you can use while working with text files. In this section, you will learn about the following file manipulation programs: sort, unique, paste, join, and split. You also learn about regular expressions and search patterns. Sort is used to rearrange the lines of a text file in either ascending or descending order, according to a sort key. You can also sort with respect to particular fields or columns in a file. The default sort key is the order of the ASCII characters, i.e. essentially alphabetically. Sort can be used like this. When used with the -u option, sort checks for unique values after sorting the records or lines. It's basically equivalent to running unique on the output of sort. Unique removes duplicate consecutive lines in a text file, and it's useful for simplifying the text display. Because unique requires that the duplicate entries must be consecutive, one often runs sort first and then pipes the output into unique. If sort is used with the -u option, it can do all this in one step. To remove duplicate entries from multiple files at once, use this command. Or you can do this one. To count the number of duplicate entries, use this command. Suppose you have a file that contains the full name of all employees and another file that lists their phone numbers and employee IDs. You want to create a new file that contains all the data listed in 3 columns: name, employee ID, and phone number. How can you do this effectively without investing too much time? Paste can be used to create a single file containing all 3 columns. The different columns are identified based on delimiters, which is spacing used to separate 2 fields. For example, delimiters can be a blank space, a tab, or an enter. In this image, a single space is used as a delimiter in all files. Paste accepts the following options: -d for the delimiters, which specify a list of delimiters to be used instead of tabs for separating consecutive values on a single line. Each delimiter is used in turn. When the list has been exhausted, paste begins again at the first delimiter. -s, which causes paste to append the data in series rather than in parallel, that is, in a horizontal rather than vertical fashion. Paste can be used to combine fields, such as name or phone number from different files, as well as combine lines from multiple files. For example, line 1 from file 1 can be combined with line 1 of file 2, and line 2 from file 1 can be combined with line 2 of file 2, and so on. To paste contents from 2 files, one can do this. And here's the syntax to use a different delimiter. Common delimiters are space, tab, and comma. Suppose you have 2 files with similar columns. You have saved employees' phone numbers in 2 files, one with their first name and the other with their last name. You want to combine the files without repeating the data of common columns. How do you achieve this? This task can be achieved using join, which is essentially an enhanced version of paste. It first checks whether the files share common fields, such as names or phone numbers, and then joins the lines in 2 files based on a common field. To combine 2 files on a common field, at the command prompt, type join file 1, file 2, and press the enter key. For example, the common field, i.e. it contains the same values, among the phone book and cities files is the phone number, and the result of joining these 2 files is shown here. Split is used to break up or split a file into equal-sized segments for easier viewing and manipulation, and it's generally used only on relatively large files. By default, split breaks up a file into 1,000-line segments. The original file remains unchanged, and a set of new files with the same name plus added prefix is created. By default, the X prefix is added. To split a file into segments, use the command split in file. To split a file into segments using a different prefix, use the command split in file and then the prefix. We will apply split to an American English dictionary file of over 99,000 lines. And in this example, we've used WC, which stands for word count, that we'll discuss shortly, to report on the number of lines in the file. And then you just type this. This will split the American English file into 100 equal-sized segments, named Dictionary XX. The last one will, of course, be somewhat smaller. Regular expressions are text strings used for matching a specific pattern or to search for a specific location, such as the start or end of a line or a word. Regular expressions can contain both normal characters or so-called meta characters, such as an asterisk or and a dollar sign. Many text editors and utilities such as vi, sed, awk, find, and grep work extensively with regular expressions. This table lists the search patterns and their usage. For example, consider the following sentence. The quick brown fox jumped over the lazy dog. Some of the patterns that can be applied to the sentence are shown here. grep is extensively used as a primary text searching tool. It scans files for specified patterns, and it can be used with regular expressions, as well as simple strings, as shown in this table. Strings is used to extract all printable character strings found in a file or files given as arguments. It's useful in locating human-readable content embedded in binary files. For text files, one can just use grep. For example, to search for the string my_string in a spreadsheet, you can use this command. And this screenshot shows a search of a number of programs to see which ones have GPL licenses of various versions. In this section, you will learn about some additional text utilities that you can use for performing various actions on your Linux files, such as changing the case of letters or determining the count of words, lines, and characters in a file. The tr utility is used to translate specified characters into other characters or to delete them. The general syntax is as follows. tr option set1 and set2. The items in the square brackets are optional. tr requires at least one argument and accepts a maximum of 2. The first, designated set1 in this example, lists the characters in the text to be replaced or removed. The second, set2, lists the characters that are to be substituted for the characters listed in the first argument. Sometimes these sets need to be surrounded by apostrophes or single quotes in order to have the shell ignore that they mean something special to the shell. It's usually safe and may be required to use the single quotes around each of the sets, as you'll see in these examples. For example, suppose you have a file named city containing several lines of a text in mixed case. To translate all lowercase characters to uppercase, at the command prompt, type cat city pipe tr a-z a-z and press the enter key. T takes the output from any command, and while sending to the standard output, it also saves it in a file. In other words, it t's the output stream from the command. One stream is displayed on the standard output, and the other is saved to a file. For example, to list the contents of a directory on the screen and save the output to a file, at the command prompt, type ls-l pipe t new file and press the enter key. Typing cat new file will then display the output of ls-l. WC, or word count, counts the number of lines, words, and characters in a file or a list of files. Options are given in this table. By default, all three of these options are active. Cut is used for manipulating column-based files and is designed to extract specific columns. The default column separator is the tab character. A different delimiter can be given as a command option. For example, to display the third column delimited by a blank space, at the command prompt, type ls-s pipe cut-d double quote space double quote, and then -F3, and then you press the enter key. You have completed Chapter 13. Let's summarize the key concepts covered. The command line often allows the users to perform tasks more efficiently than the GUI. Cat, short for concatenate, is used to read, print, and combine files. Echo displays a line of text either on standard output or to place in a file. Sed is a popular stream editor often used to filter and perform substitutions on files and text data streams. Awk is an interpreted programming language typically used as a data extraction and reporting tool. Sort is used to sort text files and output streams in either ascending or descending order. Unique eliminates duplicate entries in a text file. Paste combines fields from different files. It can also extract and combine lines from multiple sources. Join combines lines from two files based on a common field. It works only if files share a common field. Split breaks up a large file into equal-sized segments. Regular expressions are text strings used for pattern matching. The pattern can be used to search for a specific location, such as the start or end of a line or a word. grep searches the text files and data streams for patterns and can be used with regular expressions. TR translates characters, copies standard input to standard output, and handles special characters. T saves a copy of standard output to a file while still displaying at the terminal. WC, for word count, displays the number of lines, words, and characters in a file or a group of files. Cut extracts columns from a file. Less views files a page at a time and allows scrolling in both directions. Head displays the first few lines of a file or data stream or standard output. By default, it displays 10 lines. Tail displays the last few lines of a file or data stream on standard output. By default, it displays 10 lines. Strings extracts printable character strings from binary files. By the end of this chapter, you should be able to explain basic networking concepts, including types of networks and addressing issues. Configure network interfaces and use basic networking utilities such as ifconfig, IP, ping, route, and traceroute. Use graphical and non-graphical browsers such as Lynx, W3M, Firefox, Chrome, and Epiphany. Transfer files to and from clients and servers using both graphical and text mode applications such as FileZilla, FTP, SFTP, curl, and wget. A network is a group of computers and computing devices connected together through communication channels, such as cables or wireless media. The computers connected over a network may be located in the same geographical area or spread across the world. A network is used to allow the connected devices to communicate with each other, enable multiple users to share devices over the network, such as music and video servers, printers, and scanners, share and manage information across computers easily. Most organizations have both an internal network and an internet connection for users to communicate with machines and people outside the organization. The internet is the largest network in the world and can be called the network of networks. Devices attached to a network must have at least one unique network address identifier, known as the IP, or Internet Protocol address. The address is essential for routing packets of information through the network. Exchanging information across the network requires using streams of small packets, each of which contains a piece of the information going from one machine to another. These packets contain data buffers together with headers which contain information about where the packet is going to and coming from, and where it fits in the sequence of packets that constitute the stream. Network protocols and software are rather complicated due to the diversity of machines and operating systems they must deal with, as well as the fact that even very old standards must be supported. There are two different types of IP addresses available: IPv4 version 4 and IPv6 version 6. IPv4 is older and by far the most widely used, while IPv6 is newer and is designed to get past limitations inherent in the older standard and furnish many more possible addresses. IP4 uses 32 bits for addresses. There are only 4.3 billion unique addresses available. Furthermore, many addresses are allotted and reserved, but not actually used. IPv4 is considered inadequate for meeting future needs because the number of devices available on the global network has increased enormously in recent years. IPv6 uses 128 bits for addresses. This allows for 3.4 times 10 to the power of 38 unique addresses. If you have a larger network of computers and want to add more, you may want to move to IPv6 because it provides more unique addresses. However, it can be complex to migrate to IPv6. The two protocols do not always interoperate well. Thus, moving equipment and addresses to IPv6 requires significant effort and has not been quite as fast as was originally intended. We'll discuss IPv4 more than IPv6, as you're more likely to deal with it. One reason IPv4 has not disappeared is there are ways to effectively make many more addresses available by methods such as NAT, the Network Address Translation. NAT enables sharing one IP address among many locally connected computers, each of which has a unique address only seen on the local network. While this is used in organizational settings, it's also used in simple home networks. For example, if you have a router hooked up to your internet provider, such as a cable system, it gives you one externally visible address, but issues each device in your home an individual local address. A 32-bit IPv4 address is divided into four 8-bit sections called octets. So here's an example. Note that octet is just another word for byte. Network addresses are divided into 5 classes: A, B, C, D, and E. Classes A, B, and C are classified into 2 parts: network addresses, net ID, and host address, host ID. The net ID is used to identify the network, while the host ID is used to identify a host in the network. Class D is used for special multicast applications. Information is broadcast to multiple computers simultaneously. And Class E is reserved for future use. In this section, you will learn about classes A, B, and C. Class A addresses use the first octet of an IP address as their net ID, and use the other 3 octets as their host ID. The first bit of the first octet is always set to 0, so you can only use 7 bits for unique network numbers. As a result, there are a maximum of 126 Class A networks available. Not surprisingly, this was only feasible when there were very few unique networks with large numbers of hosts. As the use of the internet expanded, classes B and C were added in order to accommodate the growing demand for independent networks. Each Class A network can have up to 16.7 million unique hosts on its network. The range of host addresses is from 1.0.0.0 to 127.255.255.255. Class B addresses use the first 2 octets of their IP address as their net ID, and the last 2 octets as their host ID. The first 2 bits of the first octet are always set to binary 10. So there are a maximum of 16,384 Class B networks. The first octet of a Class B address has values from 128 to 191. The introduction of Class B networks expanded the number of networks, but it soon became clear that a further level would be needed. Each Class B network can support a maximum of 65,536 unique hosts on its network. The range of host addresses is from 128.0.0.0 to 191.255.255.255. Class C addresses use the first 3 octets of the IP address as their net ID, and the last octet as their host ID. The first 3 bits of the first octet are set to binary, 110, so almost 2.1 million Class C networks are available. The first octet of a Class C address has values from 192 to 223. These are most common for smaller networks, which don't have many unique hosts. Each Class C network can support up to 256 unique hosts. The range of host addresses is from 192.0.0.0 to 223.255.255.255. Typically, a range of IP addresses are requested from your Internet Service Provider, your ISP, by your organization's network administrator. Often, your choice of which class of IP address you are given depends on the size of your network and expected growth needs. If NAT is in operation, such as in a home network, you only get one externally visible address. You can assign IP addresses to computers over a network, either manually or dynamically. Manual assignment adds static or never-changing addresses to the network. Dynamically assigned addresses can change every time you reboot or even more often. The Dynamic Host C Configuration Protocol, DHCP, is used to assign IP addresses. Name resolution is used to convert numerical IP address values into a human-readable format known as the host name. For example, 104.95.85.15 is the numerical IP address that refers to the host name whitehouse.gov. Host names are much easier to remember. Given an IP address, you can obtain its corresponding host name. Accessing the machine over the network becomes easier when you can type the host name instead of the IP address. You can view your system's host name simply by typing hostname with no argument. The special hostname localhost is associated with the IP address 127.0.0.1 and describes the machine you are currently on, which normally has additional network-related IP addresses.
Let's get a feel for how the domain name server works on a recent Ubuntu system. So first we need to log in. And when you log in, we'll open up a command line terminal because we're going to do all our operations from the command line. So I have done that by right-clicking on the desktop, and then let me make a bigger font. I might as well go full screen while I'm at it. So there are a couple of important files on your system. One is called etcresolve.conf. Now, on older Linux systems, you didn't have all this information at the top. You just had an important thing here. Name server 127.0.053. You're more likely to find your name server is not a 127.1, which all 127 addresses are on the actual machine, but 192.168.1.1, for instance, would be a common thing. Might point to your wireless modem, which is attached to your internet service provider, for instance. Recent systems use a systemd service called systemd resolve D, which works in a more complicated way. It makes a DNS server on the local machine, which caches the results of previous searches. So we're not going to get into the details of that, but that's a recent development that you'll find on newer machines. Another important file is etc. hosts. This file is consulted before the domain name server is consulted. So you'll see, for instance, here at the bottom, we've got 2 machines on the local network. We give their IP addresses and a name that we can use to get at them. And you'll notice you can have more than one name tied to an IP address. So for instance, I could do ping Theodore, and that's going to take me to 200, or I could do ping Beaver, and it takes me to the same machine. Now, if I want to look at something which isn't specified in that file, or in fact, I can do that, host Theodore, and it will go look at the file. But if I want to get something out on the internet, I could do host linuxfoundation.org, and I'll get the both the IP4 and the IP6 addresses here of the Linux Foundation, and also information about the mail services provided by the Linux Foundation. I can do another utility for similar information is NSLookup. So I'll do that, nslookupfoundation.org, linksfoundation.org. And you see I got the same basic information, a little more compactly. I got here's the IP4 address and then the two IP6 addresses. Another utility I can use is dig. So let's do dig linuxfoundation.org. And you see I once again got the information about the IP address and then a lot more information about the search to find that server. So that's just a little bit of what you can do with DNS and some of the files that are associated with it.
Network configuration files are essential to ensure that interfaces function correctly. They are located in the /etc directory tree. However, the exact files used have historically been dependent on the particular Linux distribution and version being used. For Debian family configurations, the basic network configuration files could be found under /etc/network, while for Red Hat and SUSE family systems, one needed to inspect /etc/sysconfig/network. Modern systems emphasize the use of Network Manager, which we briefly discussed when we considered graphical system administration, rather than keep up with all the files in /etc. While the graphical versions of Network Manager do look somewhat different in different distributions, the NMTUI utility, shown here, varies almost not at all, as does the even more sparse NMCLI, or Command Line Interface utility. If you are proficient in the use of GUIs, by all means use them. If you're working on a variety of systems, the lower level utilities may make life easier. Network interfaces are a connection channel between a device and a network. Physically, network interfaces can proceed through a network interface card, or it can be more abstractly implemented as software. You can have multiple network interfaces operating at once. Specific interfaces can be brought up or activated, or brought down, deactivated, at any time. Information about a particular network interface, or all network interfaces, can be reported by the IP and ifconfig utilities, which you may have to run as the superuser, or at least give the full path name, i.e. /sbin/ifconfig. IP is newer than ifconfig and has far more capabilities, but its output is uglier to the human eye. Some new Linux distributions do not install the older NetTools package to which ifconfig belongs, and so you would have to install it if you want to use it. To view the IP address, you can do this, /sbin/IP address show. To view the routing information, /sbin/IP route show. IP is a very powerful program that can do many things. Older and more specific utilities such as ifconfig and route are often used to accomplish similar tasks. A look at the relevant man pages can tell you much more about these utilities. Ping is used to check whether or not a machine attached to the network can receive and send data, i.e. it confirms that the remote host is online and is responding. To check the status of the remote host at the command prompt, type ping and then the host name. Ping is frequently used for network testing and management. However, its usage can increase network load unacceptably. Hence, you can abort the execution of ping by typing Ctrl+C or by using the -C option, which limits the number of packets that ping will send before it quits. When an execution stops, a summary is displayed. A network requires the connection of many nodes. Data moves from source to destination by passing through a series of routers and potentially across multiple networks. Servers maintain routing tables containing the addresses of each node in the network. The IP routing protocols enable routers to build up a forwarding table that correlates final destinations with the next hop addresses. One can use the route utility or the newer IP route command to view or change the IP routing table, to add, delete, or modify specific static routes to specific hosts or networks. This table explains some commands that can be used to manage IP routing. Traceroute is used to inspect the route which the data packet takes to reach the destination host, which makes it quite useful for troubleshooting network delays and errors. By using traceroute, you can isolate connectivity issues between hops, which helps resolve them faster. To print the route taken by the packet to reach the network host, at the command prompt, type traceroute and then the address. Now let's learn about some additional networking tools. Networking tools are very useful for monitoring and debugging network problems, such as network connectivity and network traffic.
Let's get started on using more networking tools. To use more networking tools, open the command prompt. To query network interface connected to ETH2, type sudo ethtool eth0 and press enter. To display all active connections and routing tables, type netstat-r and press enter. All active connections and routing tables are displayed. To scan open ports on a network, type sudo nmap -sp 10.0.2.15/24 and press enter. The open ports on a network are displayed.
Browsers are used to retrieve, transmit, and explore information resources, usually on the World Wide Web. Linux users commonly use both graphical and non-graphical browser applications. The common graphical browsers used in Linux are Firefox, Google Chrome, Chromium, Konqueror, and Opera. Sometimes you either do not have a graphical environment to work in, or have reasons not to use it, but still need to access web resources. In such a case, you can use non-graphical browsers, such as these. Sometimes you need to download files and information, but a browser is not the best choice, either because you want to download multiple files or you want to perform the action from a command line or a script. wget is a command line utility that can capably handle the following types of downloads: large file downloads, recursive downloads, where a web page refers to other web pages and all are downloaded at once, password required downloads, and multiple file downloads. To download a web page, you simply type wget and then the URL. And then you can read the downloaded page as a local file using a graphical or non-graphical browser. Besides downloading, you may want to obtain information about a URL, such as the source code being used. Curl can be used from the command line or a script to read such information. Curl also allows you to save the contents of a web page to a file, as does wget. You can read a URL using curl URL. For example, if you want to read freecodecamp.org, type curl http://freecodecamp.org. To get the contents of a web page and store it to a file, type curl/o save.html and then the website address. The contents of the main index file at the website will be saved in save.html. Secure Shell, SSH, is a cryptographic network protocol used for secure data communication. It's also used for remote services and other secure services between two devices on the network and is very useful for administering systems which are not easily available to physically work on, but to which you have remote access. To log into a remote system using your same username, you can just type SSH, some system, and press enter. SSH then prompts you for the remote password. You can also configure SSH to securely allow your remote access without typing a password each time. If you want to run as another user, you can do either SSH-L someone some system or SSH someone at some system. To run a command on a remote system via SSH, at the command prompt you type SSH some system my command. We can also move files securely using Secure Copy, SCP, between two networked hosts. SCP uses the SSH protocol for transferring data. To copy a local file to a remote system at the command prompt, type SCP, then the local file, and then the user at the remote system, /home/user, and then you press enter. You will receive a prompt for the remote password. You can also configure SCP so that it does not prompt for a password for each transfer.
Let's do a simple demonstration of using Secure Shell and Secure Copy between two virtual machines, an Ubuntu machine and a CentOS machine. So first, from the Ubuntu machine, let's try to log into the CentOS machine. Well, first I need to know the IP address of both machines. So I can do that with IP, and I'll say brief to get a condensed output. ADDR for address show. And I can see my address on this machine is 172.168.249.133. I'll do the same command on this CentOS machine. And you see the address is the same except for the last byte or octet, which is 129. So first let's log into the CentOS machine from Ubuntu. I do SSH student at 172.16.249.129, and it's the first time I'm doing this, so it wants to make sure that I'm authentic, so I say yes. And now I have to give the password, and it's fine. I'm on the CentOS machine, as you can see from the prompt. Now in that command I really didn't have to give student at because we're using student count on both machines, but it never hurts to do that. So let me exit. Now let's do from the CentOS machine, let's copy over a directory using SCP over to the Ubuntu machine. So let me do SCP-R for recursive to get the whole directory and everything underneath it. And this time I won't. Yes, home student. I'll copy the home student directory. I won't bother saying student at. I'll just give the address 172.168.249.133, and I'll put it in the temp directory. Once again, it wants to make sure that it's authentic, so I'll say yes. And once again, I have to give the password, and it's copied over. And if I go over to the Ubuntu machine and I look in the temp directory, I'll see the account is now there. The directory is now there. So that's all there is to do a pretty simple demonstration of using Secure Shell and Secure Copy.
You have completed Chapter 14. Let's summarize the key concepts covered. The IP, or Internet Protocol, address is a unique logical network address that is assigned to a device on a network. IPv4 uses 32 bits for addresses, and IPv6 uses 128 bits for addresses. Every IP address contains both a network and a host address field. There are 5 classes of network addresses available: A, B, C, D, and E. DNS, Domain Name System, is used for converting internet domain and host names to IP addresses. The ifconfig program is used to display current active network interfaces. The commands IP, ADDR show, and IP route show can be used to view IP addresses and routing information. You can use ping to check if the remote host is alive and responding. You can use the route utility program to manage IP routing. You can monitor and debug networking problems using networking tools. Firefox, Google Chrome, Chromium, and Epiphany are the main graphical browsers used in Linux. Non-graphical or text browsers used in Linux are Lynx, and W3M. You can use wget to download web pages. You can use curl to obtain information about URLs. You can use SSH to run commands on remote systems. We've reached the end of the course. You should now have a good working knowledge of Linux from both a graphical and command line perspective. I mentioned at the beginning of the course that there is a text-based version of this course linked in the video's description. That version also has sections about the bash shell and scripting, printing, and local security principles. Those won't be relevant to everybody, but feel free to check that out if you want to learn about those topics. So good luck as you use and administer Linux.